Somewhere in the night sky, hidden within a constellation named after an ancient serpent-bearer, a star is dying, not in the slow, quiet way most stars fade. This star is dying violently, repeatedly, and on a schedule. Every 15 to 20 years, it detonates in a thermonuclear explosion so powerful that it briefly outshines 50,000 suns. And then, against all expectation, it survives. It pulls itself back together, begins feeding again, and starts building toward the next eruption. It has done this at least 7 times in recorded human history. Each time it explodes, it grows a little closer to a threshold, a boundary in physics beyond which there is no return. When it finally crosses that line, the explosion will not be a nova, it will be a supernova, and it will release more energy in a single second than our sun will produce in its entire 10 billion year lifetime. The system is called RS Ophiuchi. It sits roughly 5,000 light-years from Earth. That is about 29 quadrillion miles, a distance that sounds comfortably remote until you understand what a Type Ia supernova can do. These are among the most powerful explosions in the known universe. A single Type Ia supernova can briefly outshine an entire galaxy of 200 billion stars. The energy released is on the order of 10 to the 44 joules, a number so large that no human analogy can contain it. These detonations can sterilize planets across dozens of light-years, stripping atmospheres and bathing worlds in lethal radiation. And RS Ophiuchi is one of the closest known candidates for producing exactly this kind of event, not in some abstract, theoretical future, not in a billion years, possibly within a few 100,000 years, possibly sooner. The honest answer is that no one knows exactly when. The system does not give warnings, it gives eruptions. What makes this system so extraordinary is not simply that it might explode. Stars explode all the time. The Milky Way produces roughly 1 or 2 supernovae per century, though most are hidden behind thick curtains of interstellar dust. What makes RS Ophiuchi extraordinary is that we can watch it prepare. We can observe the fuel accumulating, layer by layer, on the surface of a dead star. We can measure the mass of the white dwarf at the heart of the system and compare it to the critical limit, a value known as the Chandrasekhar limit, set at roughly 1.4 times the mass of our Sun. We can track each eruption, study the debris flung outward at thousands of kilometers per second, and calculate how much closer the system has moved toward total annihilation. It is like watching a bomb being assembled in slow motion, 1 grain of explosive at a time, knowing that at some unknowable moment the final grain will be added, and there will be no countdown. And yet this system holds more than just the threat of destruction. It holds a key to one of the deepest mysteries in all of cosmology. Type Ia supernovae, the very kind RS Ophiuchi may one day become, are used as cosmic measuring sticks. They are called standard candles, objects whose true brightness is known, allowing astronomers to calculate how far away they are simply by measuring how dim they appear. These standard candles were the tools that allowed 2 independent teams of scientists in 1998 to discover that the expansion of the universe is not slowing down, it is speeding up. That discovery shook the foundations of physics. It led to the concept of dark energy, the mysterious force that makes up roughly 68% of everything that exists. Without understanding how systems like RS Ophiuchi work, without knowing what triggers a Type Ia supernova, and how reliable the standard candle truly is, our map of the universe begins to crack. The distances fall apart, the timeline fractures, the age of the cosmos itself becomes uncertain. By the end of tonight, you're going to understand what RS Ophiuchi is, why it erupts, how close it sits to the most violent kind of stellar death imaginable, and why this single binary star system in the constellation Ophiuchus connects to the fate of our entire understanding of the cosmos. You are going to understand what a recurrent nova truly is, what makes it different from every other explosion in the sky, and why astronomers around the world hold their breath each time this system flares back to life. You will understand the physics of thermonuclear runaway, the slow patience of accretion, and the terrifying arithmetic that governs whether a white dwarf lives through another eruption or is torn apart entirely. Most of all, you are going to understand why a small flickering point of light that most people have never heard of may be one of the most important objects in the entire galaxy. This is a story about patience and violence, about a dead star that refuses to stay quiet, about an explosion that keeps happening, each time a little more dangerous than the last, and about the moment, perhaps already written into the laws of physics, when patience runs out and the violence becomes permanent. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand what is happening inside RS Ophiuchi, we first need to understand what a star is after it dies. Not metaphorically, physically, because the object at the center of this story is not a living star. It is a corpse, a stellar remnant, a white dwarf. When a star like our Sun exhausts its hydrogen fuel, it swells into a red giant, expanding to hundreds of times its original size. It sheds its outer layers into space, forming a glowing shell of gas called a planetary nebula. And at its center, left behind like a coal after the fire has gone out, sits a dense ball of carbon and oxygen. That is a white dwarf. It no longer generates energy through nuclear fusion. It simply glows from residual heat, slowly cooling over billions of years, like a ceramic plate removed from an oven. Eventually, in the distant future, it will cool to the point where it no longer emits visible light at all, becoming what is sometimes called a black dwarf. But no black dwarf has ever formed in the history of the universe. The cosmos is simply not old enough. At 13.8 billion years old, the universe has not had time for even the oldest white dwarfs to fade completely. A white dwarf is a strange object. It packs roughly the mass of the Sun into a volume about the size of Earth. To put this in perspective, a teaspoon of white dwarf material would weigh approximately 5.5 metric tons. That is heavier than a full-sized elephant, compressed into a volume smaller than a sugar cube. The density is nearly incomprehensible. It is held up not by thermal pressure, the way a normal star is, but by something called electron degeneracy pressure. This is a quantum mechanical effect. The electrons in the material are packed so tightly that the Pauli exclusion principle, a law of quantum mechanics that forbids two identical particles from occupying the same state, resists further compression. The star is held up by the stubbornness of electrons refusing to be pushed into the same quantum state. It is a balance between gravity pulling inward and quantum mechanics pushing outward, and that balance has a limit. In 1930, a young Indian physicist named Subramanian Chandrasekhar, barely 20 years old, and travelling by steamship from Madras to Cambridge, performed a calculation that would reshape our understanding of stellar death. He showed that there is a maximum mass a white dwarf can sustain before electron degeneracy pressure fails. That mass is approximately 1.44 times the mass of the Sun. Above that threshold, the electrons can no longer hold back gravity. The star collapses. This value is now called the Chandrasekhar limit, and it is one of the most important numbers in all of astrophysics. It is the line between a white dwarf that quietly cools for eternity and one that detonates in the most violent explosion a single star can produce. Chandrasekhar would eventually receive the Nobel Prize in Physics in 1983 for this, and related work on the structure of stars. But at the time, his ideas were dismissed and even ridiculed by the great Sir Arthur Eddington, one of the most prominent astrophysicists of the era. Eddington could not accept that nature would allow a star to collapse beyond this point. He was wrong. Now, most white dwarfs sit comfortably below the Chandrasekhar limit. Our own Sun, when it eventually becomes a white dwarf in roughly 5 billion years, will have a remnant mass of about 0.54 solar masses, nowhere near the danger zone. It will cool quietly, peacefully, for trillions of years. But not all white dwarfs are so isolated. Some exist in binary systems, pairs of stars locked in mutual gravitational orbit. And when a white dwarf has a close companion, particularly a large bloated companion like a red giant, something dangerous begins to happen. This is where the story of RS Ophiuchi begins to take shape. In this system, a white dwarf orbits a red giant star at close range. The orbital period is approximately 456 days, meaning the two stars complete one full orbit around their shared center of mass in roughly a year and 3 months. They are close enough that the gravitational pull of the white dwarf can strip material from the outer layers of the red giant. This process is called accretion. The red giant, being enormous and loosely bound, is already shedding mass through a powerful stellar wind. But in the region between the two stars, there is a point where the gravitational pull of the white dwarf exceeds that of the red giant. Material that crosses this boundary, called the inner Lagrangian point or simply the L1 point, falls toward the white dwarf. It spirals inward, forming a swirling disk of gas called an accretion disk, and eventually settles onto the surface of the white dwarf. To visualize the scale of this process, consider the following. If the white dwarf were the size of a marble, about 1 centimeter across, then the red giant would be the size of a large beach ball, perhaps 60 centimeters in diameter. The distance between them in this scaled model would be roughly 3 meters. The marble is stealing material from the beach ball across that gap, slowly, steadily, grain by grain. Now imagine that the marble is not just any marble. It is a marble made of material so dense that it weighs as much as a truck, and it is gaining weight. The material that accumulates on the white dwarf's surface is primarily hydrogen. Hydrogen is the simplest and most abundant element in the universe, and it is also the most eager to undergo nuclear fusion when subjected to sufficient temperature and pressure. As the hydrogen piles up on the white dwarf's surface, it is compressed by the dwarf's enormous gravity. The temperature at the base of this accumulated layer rises, and at some point, when enough hydrogen has been deposited and the conditions at the base reach approximately 10 million to 20 million degrees Celsius, something extraordinary happens. The hydrogen ignites, not gradually, like a candle flame catching, violently, all at once. The entire accumulated layer detonates in a thermonuclear explosion that blows the material outward at speeds of thousands of kilometers per second. This is a nova. The word comes from the Latin for new, because to ancient observers, a nova looked like a new star appearing in the sky where none had been before. In reality, it is not a new star. It is an old dead star erupting in stolen fuel. The nova does not destroy the white dwarf. The explosion occurs only on the surface. The core remains intact. After the eruption, the white dwarf settles down, the accretion process resumes, and hydrogen begins to pile up once more. The cycle begins again. Most novae are one-time events, at least on human timescales. A classical nova might erupt once and then not again for tens of thousands or even hundreds of thousands of years. The recurrence time depends on the mass of the white dwarf and the rate at which it accretes material. A low-mass white dwarf with a slow accretion rate might take 1 million years to accumulate enough hydrogen to trigger another eruption. But a high-mass white dwarf, one sitting dangerously close to the Chandrasekhar limit, with a high accretion rate from a generous companion, can cycle much faster. And this is what makes recurrent novae special. A recurrent nova is defined as a nova system that has been observed to erupt more than once within the span of recorded human history. There are fewer than 10 confirmed recurrent novae in the entire Milky Way galaxy. RS Ophiuchi is one of them, and it is the one that erupts most frequently. Its recorded eruptions occurred in 1898, 1933, 1958, 1967, 1985, 2006, and 2021. That is 7 confirmed eruptions in just over a century. The average interval between eruptions is roughly 15 to 20 years, though the spacing is not perfectly regular. To appreciate how unusual this is, consider the following comparison. If the history of the Milky Way were compressed into a single calendar year, with the galaxy forming on January 1st and the present moment falling on December 31st at midnight, then the entire span of recorded human civilization, all 10,000 years of it, would fit into the final second of that year. And within that final second, RS Ophiuchi has erupted 7 times, 7 thermonuclear explosions in the blink of a cosmic eye. Most novae erupt once in 1 million years. RS Ophiuchi erupts once in a generation. Something about this system is different. The difference lies in 2 factors. First, the white dwarf in RS Ophiuchi is massive. Estimates place its mass at approximately 1.2 to 1.4 solar masses. That is perilously close to the Chandrasekhar limit of 1.44 solar masses. A white dwarf this heavy requires far less accumulated hydrogen to trigger a thermonuclear runaway. where a lighter white dwarf might need to accumulate a layer of hydrogen equivalent to 1/10,000th of a solar mass. A heavy white dwarf near the Chandrasekhar limit might need only 1/1,000,000th of a solar mass. The critical fuel load is smaller because the surface gravity is stronger, the compression is more intense, and the ignition conditions are reached sooner. Second, the accretion rate is high. The red giant companion in the RS Ophiuchi system is losing mass at a significant rate, and a substantial fraction of that mass is being captured by the white dwarf. Estimates suggest the accretion rate is on the order of 1/10,000,000th of a solar mass per year. That might sound minuscule, but over 15 to 20 years, it adds up to enough fuel to trigger the next eruption. There is a question buried inside these numbers. A critical question. If the white dwarf is so close to the Chandrasekhar limit, and it is gaining mass with each eruption cycle, then is it getting closer to the limit over time? Is each eruption leaving behind a little more mass than was there before the accretion began? Or does each eruption blow away all of the accumulated material, resetting the clock to zero? This question is not academic, it is the question. Because if the white dwarf is gaining net mass, then it is on a one-way path toward the Chandrasekhar limit. And when it crosses that limit, the explosion will not be a surface event. It will be a total detonation. The entire white dwarf, all 1.4 solar masses of carbon and oxygen, will undergo thermonuclear fusion simultaneously. The star will be completely destroyed. No remnant, no neutron star, no black hole, just an expanding shell of debris and energy, briefly outshining every other star in the galaxy combined. That is a Type Ia supernova. And RS Ophiuchi may be building toward one right now. Consider one more scaled comparison before we move on. If you were to take all the energy released by our Sun in a single day, a quantity of energy that is already staggering, roughly 3.8 times 10 to the 26 watts, enough to power every device on Earth for millions of years, and if you were to somehow bottle that energy and set it aside, you would need to collect the Sun's daily output for about 10 billion years to match the energy released in a single Type Ia supernova. 10 billion years of solar output, released in a few seconds. That is the scale of what RS Ophiuchi might one day become, and it sits 5,000 light-years away. In galactic terms, that is close. The Milky Way stretches 100,000 light-years across. RS Ophiuchi is within 5% of the distance from the center to the edge. It is in our neighborhood. To fully grasp the significance of what happens on the surface of a white dwarf during a nova, it helps to understand the physics of thermonuclear runaway. On Earth, nuclear fusion requires carefully controlled conditions. The tokamak reactors and laser ignition facilities that scientists have spent decades building are designed to contain plasma at temperatures exceeding 100 million degrees Celsius, forcing hydrogen nuclei close enough together for the strong nuclear force to bind them. The process is difficult, unstable, and extraordinarily hard to sustain. But on the surface of a white dwarf, nature does the work effortlessly. The gravity is so intense, roughly 300,000 times that of Earth, that the accumulated hydrogen is compressed to extreme densities. And because the white dwarf's surface is essentially a solid, rigid lattice of degenerate matter, the hydrogen cannot expand as it heats up. On a normal star, heating causes the gas to expand, which cools it and regulates the fusion process. This is called the thermostat effect, and it keeps normal stars from exploding. But on a white dwarf, the degenerate surface does not expand in response to heating. The temperature rises without relief, and when it reaches the ignition point, the fusion reaction runs away. It cascades across the entire surface in a matter of seconds. Every atom of accumulated hydrogen fuses almost simultaneously. The result is a blast that ejects the outer layer of the white dwarf at velocities between 3,000 and 10,000 kilometers per second. For context, the speed of sound in air at sea level is about 340 meters per second. The fastest bullet ever fired by a human weapon travels at roughly 1.7 kilometers per second. The material expelled by a nova travels thousands of times faster than a bullet, and the luminosity spike is equally extreme. RS Ophiuchi typically sits at around 12th magnitude in its quiet state, far too faint to see with the naked eye. During eruption, it brightens to roughly 5th magnitude, or even 4th magnitude, making it just visible without a telescope. That represents a change in brightness by a factor of roughly 1,000 to 10,000. In a matter of hours, the system flares from invisibility to naked eye visibility. If the sun were the size of a basketball, roughly 24 centimeters in diameter, then the white dwarf in RS Ophiuchi would be the size of a small pea, perhaps 1 centimeter across. But that pea would weigh as much as the basketball. And the red giant companion, in this same model, would be a sphere large enough to fill a small room, perhaps 2 to 3 meters across. The pea is stealing material from the room-sized sphere, growing slightly heavier with each passing month, until finally the stolen material detonates on its surface. The pea survives. The room-sized sphere barely notices the theft. And the process starts over. The constellation Ophiuchus, where RS Ophiuchi resides, has an ancient pedigree. The name means serpent-bearer in Greek, and the constellation is associated with Asclepius, the mythological healer who was said to have learned the secrets of life and death from a serpent. There is a grim poetry in the fact that a star system embodying both death and resurrection, explosion and renewal, lives within the boundaries of the serpent-bearer's domain. Ophiuchus sits along the plane of the Milky Way, in a rich star field thick with dust and nebulae. RS Ophiuchi is not easy to find. Even during eruption, it is a modest point of light among millions. But to those who know where to look, and to the automated survey telescopes that now patrol the sky every night, its awakening is unmistakable. The study of novae has a long and distinguished history. The Chinese recorded guest stars as early as 134 BCE, and many of these were likely novae or supernovae. In Europe, the Danish astronomer Tycho Brahe observed a brilliant new star in 1572, and 6 years later, Johannes Kepler saw another in 1604. Both were supernovae, not novae, but they established the idea that the heavens were not permanent and unchanging, as Aristotle had claimed. The distinction between novae and supernovae was not understood until the 1930s, when the Swiss astronomer Fritz Zwicky and the German-American Walter Baade proposed that supernovae were fundamentally different events, vastly more energetic, and involving the complete destruction or collapse of a star. The first recorded eruption of RS Ophiuchi was noted in 1898 by Williamina Fleming, one of the remarkable women astronomers working at the Harvard College Observatory. Fleming was part of a group sometimes called the Harvard Computers, women who were hired to catalogue and analyse photographic plates of the sky. Her discovery of RS Ophiuchi's eruption on those glass plates was one of many contributions she made to astronomy, contributions that were often under-recognized during her lifetime. The star was subsequently observed in eruption again in 1933, and its recurrent nature began to emerge. By the time it erupted in 1958, astronomers understood that they were dealing with something rare and important, a nova that repeats on a human timescale. The significance of that short recurrence time cannot be overstated. It means the white dwarf in the system is gaining fuel quickly. It means the conditions for thermonuclear ignition are being met in just 15 to 20 years, a period so short that individual astronomers can witness multiple eruptions within a single career. It means we can study the system across several cycles, comparing one eruption to the next, tracking changes, looking for signs that the white dwarf is growing heavier. And most importantly, it raises the central question, the question that drives all modern research on RS Ophiuchi, the question that connects this obscure binary star system to the most fundamental problems in physics. Is the white dwarf gaining mass? And if it is, how long until it reaches the Chandrasekhar limit? To appreciate the stakes of this question, consider what happens at the Chandrasekhar limit itself. Below the limit, the white dwarf is stable. The quantum mechanical pressure of degenerate electrons holds it up, but as mass is added, the electrons are forced into higher and higher energy states. They begin to move at speeds approaching the speed of light, roughly 300,000 kilometers per second. At this point, the special theory of relativity changes the game. Relativistic electrons provide less resistance to further compression. The pressure support weakens, and at exactly 1.44 solar masses, the balance tips, gravity wins, the core begins to collapse. But unlike a massive star, where the core collapses to form a neutron star or black hole, The white dwarf's collapse triggers something different. The carbon and oxygen in the core, which have been sitting inert for billions of years, are suddenly forced together at such extreme temperatures and densities that they undergo nuclear fusion. Carbon fuses to neon and magnesium, oxygen fuses to silicon and sulfur, silicon fuses to nickel, and because the entire core is degenerate, the thermostat effect still does not work. The fusion runs away, propagating through the entire star at a significant fraction of the speed of sound in the material, perhaps 10,000 kilometers per second. In less than 2 seconds, the entire white dwarf is consumed. Roughly 1.4 solar masses of matter is converted to heavier elements and pure energy. The star is unbound, completely destroyed. Nothing is left behind except an expanding cloud of radioactive debris. This is the mechanism of a Type Ia supernova. It is clean, it is complete. And because the trigger is always the same, the Chandrasekhar limit, the total energy released, is remarkably consistent from one event to the next. This consistency is what makes Type Ia supernovae so valuable as standard candles. Their peak luminosity is nearly the same every time, about 5 billion times the luminosity of the Sun. By measuring how bright a Type Ia supernova appears from Earth, and comparing that apparent brightness to the known true brightness, astronomers can calculate the distance to the host galaxy with remarkable precision. This technique has been used to measure distances across billions of light years. It was this technique that, in 1998, revealed the accelerating expansion of the universe and the existence of dark energy. The connection between RS Ophiuchi and the accelerating expansion of the universe may seem remote, but it is direct. If we do not understand the progenitor systems of Type Ia supernovae, if we do not know what triggers them, how their brightness varies, and whether the standard candle is truly standard, then every distance measurement based on them becomes uncertain. And with it, our understanding of dark energy, the dominant component of the cosmos. RS Ophiuchi, then, is not merely a curiosity. It is a laboratory, a natural experiment unfolding in real time. Each eruption provides a fresh dataset. Each recovery period allows astronomers to study the accretion process as it restarts. And each new instrument that comes online, from the Chandra X-ray Observatory to the Neil Gehrels Swift Observatory to the Fermi Gamma Ray Space Telescope, reveals new details that were invisible to earlier generations. The 2006 eruption of RS Ophiuchi was one of the most intensively observed nova events in history, studied across the entire electromagnetic spectrum from radio waves to gamma rays. The 2021 eruption was observed by even more sophisticated instruments, including the High-Energy Stereoscopic System, or HESS, an array of gamma-ray telescopes in Namibia, which detected very high-energy gamma rays from the nova for the first time. These observations changed our understanding of particle acceleration in nova shocks and opened an entirely new window onto the physics of these explosions. Every eruption teaches us something new, and every eruption brings the white dwarf one step closer to its final reckoning. But what scientists discovered about this system, through more than a century of patient observation, was worse than anyone expected. The story of RS Ophiuchi, like many stories in astronomy, is a story of patience. Not the patience of the stars, though they have plenty, but the patience of the people who watch them. For more than a century, astronomers have been tracking this system, recording its eruptions, measuring its properties, and trying to answer a deceptively simple question: is the white dwarf getting heavier? That question sounds straightforward. It is not. The problem begins with the eruptions themselves. Each time RS Ophiuchi detonates, it expels material at enormous velocities. The outer layer of accumulated hydrogen, along with some material dredged up from the white dwarf's surface, is flung outward in a rapidly expanding shell. This ejector contains not only hydrogen and helium from the accreted material, but also carbon, oxygen, and nitrogen from the white dwarf's outer layers. The total mass ejected in a single eruption has been estimated at roughly 1/10 millionth to 100 millionth of a solar mass. That is a small number in absolute terms, but it is critically important for the mass budget. Here is the crux. Between eruptions, the white dwarf accretes perhaps 1 to 2 millionths of a solar mass of hydrogen from the red giant. When the nova erupts, some of that mass is expelled. The question is, whether all of the accreted mass is expelled, or whether the white dwarf retains a fraction. If it retains even a small fraction, say 10 to 20% of the accreted material, then over many eruption cycles, the white dwarf's mass will slowly increase. It will creep toward the Chandrasekhar limit. Each cycle nudges it closer. The margins are tiny, but the time available is enormous. For decades, the answer was unclear. Some models suggested that classical novae actually erode the white dwarf, expelling more mass than was accreted by dredging up material from the carbon-oxygen core. In these models, the white dwarf is slowly losing mass with each eruption. It is not approaching the Chandrasekhar limit, it is retreating from it. If this were true for RS Ophiuchi, the system would never produce a Type ER supernova. It would just continue erupting indefinitely, slowly wearing down the white dwarf over millions of years. But other models told a different story. In systems with very high accretion rates and very massive white dwarfs, the hydrogen ignites quickly and efficiently. The burning layer is thin, and the explosion, while violent, does not penetrate deeply into the white dwarf structure. Less core material is dredged up. More of the accreted mass is processed into helium through nuclear fusion and retained on the surface. In these models, the white dwarf gains a small but positive amount of mass with each cycle. The net gain might be only a few percent of the accreted mass, but it is positive. The arrow points in one direction, toward the limit. The 1985 eruption of RS Ophiuchi was a turning point in this debate. It was observed with more instruments and greater sensitivity than any previous eruption of the system. Astronomers used optical telescopes, radio telescopes, and the first generation of space-based X-ray observatories to study the event. What they found was striking. The ejector velocities were high, exceeding 4,000 kilometers per second. The ejected mass was relatively low, and the X-ray emission, which traces the shocked, heated gas as the ejector slam into the surrounding medium, revealed a complex, asymmetric structure, suggesting that the explosion was interacting with a dense, stellar wind from the red giant. But the most important finding from the 1985 eruption was the estimate of the white dwarf's mass. By analyzing the light curve, the spectral evolution, and the dynamics of the ejector, several research groups concluded that the white dwarf was extremely massive. The estimates ranged from 1.2 to 1.4 solar masses. Some analyses pushed the number even higher, to 1.35 or 1.37 solar masses. These numbers placed the white dwarf within a hair's breadth of the Chandrasekhar limit. A white dwarf at 1.35 solar masses needs to gain only 0.09 solar masses to reach 1.44. That might sound like a lot, but at an accretion rate of 1/1,000,000th of a solar mass per year, with even modest retention, it could happen in less than 1,000,000 years. In astronomical terms, that is tomorrow, and it gets worse. The 2006 eruption provided even more detailed data. By this time, the Chandra X-ray Observatory was operational, as was the SWIFT satellite, which could respond to transient events within hours and observe in X-ray and ultraviolet wavelengths simultaneously. The SWIFT observations of the 2006 eruption were particularly revealing. They showed that the supersoft X-ray source, a signature of residual nuclear burning on the white dwarf's surface, appeared just 26 days after the eruption began. This was extraordinarily fast. In typical novae, the supersoft phase appears months or even years after eruption because the ejector take that long to thin out enough for the X-rays to escape. The rapid appearance of the supersoft source in RS Ophiuchi meant two things. First, the ejected mass was very low, confirming that the explosion was not throwing off much material. Second, nuclear burning on the white dwarf's surface continued for an extended period after the eruption, processing additional hydrogen into helium and depositing it onto the dwarf's surface. This extended burning was effectively free mass addition. Material that had not been expelled was being quietly fused and incorporated into the white dwarf structure. The implication was clear. The white dwarf in RS Ophiuchi is almost certainly gaining mass. The 2021 eruption, detected on August 8th of that year, brought yet another revelation. This time, the HESS Gamma Ray Telescope Array in Namibia detected very high-energy gamma rays from the system, photons with energies exceeding 100 billion electron volts. This was the first time a nova had ever been detected at such extreme energies. The detection meant that the shock wave produced by the eruption was accelerating particles, likely protons, to near the speed of light. These cosmic rays were then colliding with the dense stellar wind of the red giant, producing gamma rays through a process called hadronic interaction. The discovery was published in the journal Science in 2022 by a large international collaboration, and it transformed our understanding of novae as particle accelerators. But beyond the gamma ray physics, the 2021 eruption confirmed the basic parameters of the system. The white dwarf remained extremely massive. The ejected mass remained low. The accretion rate remained high. Every eruption was telling the same story. The white dwarf is heavy, it is gaining weight, and the clock is ticking. Now, to be fair, there is genuine scientific uncertainty here. The exact mass of the white dwarf is difficult to measure precisely. Orbital mechanics can constrain the total mass of the binary system, but separating the individual masses of the white dwarf and the red giant requires additional assumptions about the system's inclination and other parameters. Different research groups, using different methods and different datasets, have arrived at slightly different numbers. Some estimates place the white dwarf at 1.2 solar masses, which is still very heavy but gives more room before the Chandrasekhar limit. Others push it to 1.37 or even higher. The uncertainty is real, but even the most conservative estimates place the white dwarf in the danger zone. There is also the question of whether the Chandrasekhar limit is exactly 1.44 solar masses. The precise value depends on the composition of the white dwarf and the rate at which it is rotating. Rapidly rotating white dwarfs can support slightly more mass. Some theoretical models allow super-Chandrasekhar white dwarfs with masses up to 2 solar masses or beyond. If the white dwarf in RS Ophiuchi is rotating rapidly, which is plausible given the angular momentum transferred during accretion, then the true limit might be higher, and the system might be farther from the edge than it appears. This is a legitimate argument. But it is also an argument at the margins. The white dwarf is still one of the most massive known. The accretion is still ongoing. The fundamental trajectory has not changed. Something else is worth considering. The red giant in the RS Ophiuchi system is itself evolving. Red giants do not remain red giants forever. They are in a late phase of stellar evolution, burning helium in a shell around an inert core, and they will eventually shed their outer layers entirely, leaving behind their own white dwarf remnant. When the red giant loses enough mass, the accretion onto the white dwarf will slow or stop. If this happens before the white dwarf reaches the Chandrasekhar limit, then the system will never produce a Type ER supernova. It will become a pair of white dwarfs orbiting each other, slowly spiraling inward due to the emission of gravitational waves, until eventually, perhaps billions of years later, they merge. And that merger might itself produce a Type Ia supernova through an entirely different mechanism. But that is a story for another time. The critical race, then, is between the evolution of the red giant and the growth of the white dwarf. Will the white dwarf gain enough mass before its fuel supply runs out? This question has no definitive answer yet, but the data from each eruption from 1898 through 2021 lean in one direction. The white dwarf appears to be winning. Let us pause for a moment and consider what it means for a white dwarf to approach the Chandrasekhar limit. We have used numbers and abstractions, so let us try to make it concrete. The white dwarf in RS Ophiuchi has a diameter of roughly 8,000 to 12,000 kilometers. That is comparable to Earth, which has a diameter of about 12,742 kilometers. But this Earth-sized object has a mass roughly 1.3 times that of the Sun. Our Sun has a diameter of about 1.4 million kilometers, so the white dwarf has crushed a Sun's worth of material into an Earth-sized ball. If you could stand on its surface, and you cannot because you would be instantly flattened by the gravity and incinerated by the temperature, you would weigh roughly 70 million times what you weigh on Earth. A single grain of sand on the surface of this white dwarf would weigh as much as a small car. And this object, this impossibly dense marble of degenerate matter, is slowly, steadily, inexorably gaining mass from its bloated companion, layer by layer, eruption after eruption. Each time it explodes, it sheds some weight. But not enough. Each time it recovers, it gains more than it lost. The margin is thin, perhaps a few percent of the accreted mass per cycle. But it is positive, and over thousands or tens of thousands of eruption cycles, the increments add up. The history of observation tells us that the eruptions are getting more closely spaced. The gaps between the 1898 and 1933 eruptions was 35 years. Between 1933 and 1958, 25 years. Between 1958 and 1967, only 9 years. Between 1967 and 1985, 18 years. Between 1985 and 2006, 21 years. Between 2006 and 2021, 15 years. The pattern is irregular, and it would be a mistake to read too much into the specific numbers. Some eruptions may have been missed, particularly in the early 20th century, when sky monitoring was far less comprehensive. The 9-year gap between 1958 and 1967 is suspiciously short, and may indicate that one of those eruptions was unusually weak, or that both followed a period of unusually high accretion. But the overall trend, if there is one, suggests a system that is erupting more frequently as the white dwarf grows heavier. A heavier white dwarf needs less fuel to erupt. Less fuel takes less time to accumulate. The eruptions come faster. The clock accelerates. There is a concept in dynamical systems called a positive feedback loop. The more the system does something, the more it is inclined to do it again faster. RS Ophiuchi may be in such a loop. As the white dwarf gains mass, its surface gravity increases. Higher surface gravity means the accreted hydrogen is compressed more quickly. More rapid compression means the ignition conditions are reached sooner. Sooner ignition means shorter intervals between eruptions. And shorter intervals, if the retention rate per eruption is roughly constant, mean that the total mass gain per unit time increases as well. The system is not just approaching the Chandrasekhar limit, it may be accelerating toward it. To understand just how sensitive this balance is, think of it this way. Imagine you are filling a bathtub, but the drain is partially open. Water flows in from the tap and drains out through the plug hole simultaneously. If the tap runs faster than the drain, the water level rises. If the drain is faster, the level drops. Now imagine that as the water level rises, the tap opens slightly wider. The higher the level, the faster it fills. That is the positive feedback at work. At some point, the water reaches the rim and spills over. In the case of RS Ophiuchi, the rim is the Chandrasekhar limit, and the overflow is not water. It is a thermonuclear detonation that destroys the entire tub. Something is wrong with our assumptions if we think this system is safe. The numbers do not add up to a stable repeating cycle that continues forever. They add up to a trajectory with an endpoint. The only uncertainty is the timing. Consider the broader context of recurrent novae. RS Ophiuchi is not the only system of its kind, though it is the most famous and the most studied. Other recurrent novae include T. Coronae borealis, which erupted in 1866 and again in 1946, an interval of 80 years. U. Scorpiae has the shortest known recurrence period, with eruptions observed in 1863, 1906, 1936, 1979, 1999, and 2010. T. Pixtis erupted 5 times between 1902 and 1966, then fell silent for 45 years before erupting again in 2011. Each of these systems tells a slightly different story, but they all share the same fundamental architecture. A massive white dwarf, a generous companion, an accretion rate high enough to trigger eruptions on human timescales, and a question, always the same question, about whether the white dwarf is gaining or losing mass. What makes RS Ophiuchi stand out among these systems is the combination of its very massive white dwarf, its generous red giant companion, and its relatively short eruption cycle. T. Coronae borealis has a similarly massive white dwarf, but its longer 80-year cycle suggests a lower accretion rate or a higher critical mass for ignition. U. Scorpii erupts even more frequently, roughly every 10 years, and its white dwarf is also believed to be near the Chandrasekhar limit. But U. Scorpii's companion is a main sequence star, not a red giant, and the accretion process is different. RS Ophiuchi occupies a particular niche in the parameter space of recurrent novae that makes it one of the strongest candidates for a future Type Ia supernova. The physics of the eruption itself deserves a closer look, because the details reveal just how extreme the conditions are. When the accumulated hydrogen layer on the white dwarf surface reaches the critical temperature of roughly 10 to 20 million degrees Celsius, the dominant nuclear reaction is the carbon-nitrogen-oxygen cycle, often abbreviated as the CNO cycle. This is the same fusion process that powers massive stars, where carbon acts as a catalyst, facilitating the fusion of hydrogen into helium through a series of reactions involving nitrogen and oxygen isotopes. The CNO cycle is highly temperature sensitive. A small increase in temperature produces a dramatic increase in the reaction rate. This sensitivity is what drives the thermonuclear runaway. Once the critical temperature is reached, the reaction rate soars, which raises the temperature further, which accelerates the reaction further. The feedback is explosive. In a matter of seconds, the temperature at the base of the hydrogen layer exceeds 100 million degrees. The fusion reactions become so intense that the energy cannot be transported outward fast enough through normal processes like radiation or convection. The layer detonates. The immediate aftermath of the eruption is dramatic. The ejected shell slams into the pre-existing wind from the red giant companion, creating a powerful shock wave. This shock heats the surrounding gas to temperatures of millions of degrees, producing intense X-ray emission. The shock also accelerates particles to relativistic energies, generating radio emission through synchrotron radiation, and, as the 2021 HS observations showed, very high-energy gamma rays through hadronic interactions. The nova remnant evolves rapidly over the following weeks and months. The ejecta thin out as they expand, the shock weakens, the X-ray emission fades, and eventually the system returns to its quiet state, with the white dwarf once again accreting material from the red giant. The observation of RS Ophiuchi across the electromagnetic spectrum has revealed the anatomy of a nova eruption in extraordinary detail. In radio wavelengths, observers have tracked the expanding shell and measured its velocity. In the infrared, they have detected emission from dust formed in the cooling ejecta. In optical wavelengths, they have monitored the light curve and spectral evolution. In the ultraviolet and X-ray bands, they have traced the evolution of the shocked gas and the supersoft source. And now, in gamma rays, they have probed the most energetic processes occurring in the eruption. Each wavelength tells a different part of the story. Together, they compose a remarkably complete picture. And the picture is one of a system on the edge. A white dwarf approaching the Chandrasekhar limit, an accretion rate high enough to trigger frequent eruptions, a retention rate that appears to be positive, and a companion star that will continue providing fuel for at least hundreds of thousands of years. The ingredients for a Type Ia supernova are present. The process is underway. The only missing variable is time. There is one more piece that deserves attention. In 2011, a team of astronomers used the Very Long Baseline Array, a network of 10 radio telescopes spread across the United States from Hawaii to the Virgin Islands, to study the 2006 eruption at extraordinary resolution. What they observed was the expanding shockwave resolved into a bipolar structure. The ejecta were not expanding uniformly in all directions. They were concentrated into two lobes, one moving toward us and one moving away, suggesting that the accretion disk and the equatorial density of the red giant's wind were shaping the explosion. This bipolar structure confirmed that the environment around the white dwarf is complex, and that the interactions between nova ejecta, accretion disk, and stellar wind play a crucial role in determining how much mass is retained or lost. The trajectory is clear. RS Ophiuchi is a system in which a dead star is slowly being resurrected toward one final, catastrophic detonation. Each eruption is both a release and an accumulation. Each explosion is a step toward a much larger ending, and we are watching it happen in real time. Let us take a moment to consider the timescales involved, because they reveal a tension between human experience and cosmic reality. The interval between eruptions of RS Ophiuchi is roughly 15 to 20 years. That is about the span of a human generation. A child born during one eruption will be a young adult when the next occurs. An astronomer who witnesses their first RS Ophiuchi eruption as a graduate student may see 4 or 5 more before they retire. This is an extraordinarily fast timescale by the standards of stellar evolution, where most changes occur over millions or billions of years. And yet, the timescale for the white dwarf to actually reach the Chandrasekhar limit, if it is gaining mass, is vastly longer. Even in the most optimistic models, the white dwarf needs to gain perhaps 0.04 to 0.2 solar masses. At a net gain of perhaps 1 billionth of a solar mass per year, it would take tens of millions to hundreds of millions of years. In the most pessimistic models, it could take 1 billion years or more. This creates an unusual psychological situation. We can see the process happening, we can measure it, we can track it from eruption to eruption. But the conclusion, the actual Type Ia supernova, if it happens at all, is separated from us by a chasm of time that no human mind can truly fathom. 1 million years ago, our ancestors were Homo erectus, chipping stone tools on the African savanna. 1 million years from now, it is impossible to guess what descendants of humanity might look like, or whether they will exist at all. RS Ophiuchi operates on timescales that span the rise and fall of entire species. And yet, there is another possibility, a possibility that keeps a small number of astronomers alert every time the system shows signs of activity. What if the estimates are wrong? What if the white dwarf is closer to the Chandrasekhar limit than current measurements suggest? What if the retention rate is higher than current models predict? What if the next eruption is not a nova at all, but the beginning of the end? The probability is low for any given eruption, vanishingly low, but it is not zero, and that non-zero probability, multiplied by the magnitude of the event, is what makes RS Ophiuchi one of the most carefully monitored systems in the sky. If the white dwarf in RS Ophiuchi were to undergo a Type Ia supernova today, the effects on Earth would be modest. At 5,000 light-years, we are well outside the danger zone for direct harm. A Type Ia supernova would need to be within roughly 50 light-years to pose a serious threat to Earth's biosphere, and some estimates place the danger zone even closer at 25 to 30 light-years. At 5,000 light-years, the supernova would appear as a brilliant point of light in the sky, perhaps as bright as the full moon or even brighter for a few weeks. It would be visible in daylight. It would cast shadows at night. It would be the most spectacular astronomical event witnessed by living humans, but it would not harm us. The scientific value, however, would be incalculable. A Type Ia supernova at 5,000 light-years would be the closest observed in centuries, possibly in recorded history. The last supernova seen in the Milky Way was Kepler's supernova in 1604, and it was a Type Ia that occurred roughly 20,000 light-years away. A supernova 4 times closer would be 4 times easier to study. Modern instruments, from space telescopes to neutrino detectors to gravitational wave observatories, could capture details that have never been observed before. It would revolutionize our understanding of Type Ia supernovae, validate or overturn decades of theoretical models, and calibrate the standard candle with unprecedented precision. The irony is that the same event that would be scientifically priceless is also the event that is most dangerous in the long run. If RS Ophiuchi produces a Type Ia supernova, it will confirm that the single degenerate channel, where a white dwarf accretes mass from a companion until it crosses the Chandrasekhar limit, actually works. That would settle one of the longest-running debates in astrophysics, but it would also raise uncomfortable questions about how many other similar systems exist, how close they might be, and how frequently this process occurs in galaxies like our own. The Milky Way contains roughly 400 billion stars. Binary systems account for perhaps half of all star systems. Among those, some fraction contain white dwarfs with suitable companions. The exact number of potential Type Ia supernova progenitors in our galaxy is not known, but estimates suggest there may be several dozen systems in various stages of the process, most of them too faint or too distant to detect. RS Ophiuchi is one we can see. There may be others we cannot, and this raises a point that is often overlooked in popular discussions of stellar explosions. The danger of a nearby supernova is not just in the explosion itself, it is in the uncertainty. we do not have a complete census of potential Type Ia progenitors within a few hundred light-years of Earth. Our surveys are improving with missions like the European Space Agency's Gaia satellite, which has catalogued the positions, motions, and distances of nearly 2 billion stars in the Milky Way. But many white dwarfs are faint, and many binary systems are difficult to characterize without detailed spectroscopic study. The closest known white dwarf, Sirius B, orbits the brightest star in the night sky at a distance of only 8.6 light-years from Earth. It is not a Type Ia progenitor. Its companion, Sirius A, is a main sequence star that is not losing mass to the white dwarf in any significant way. But the existence of a white dwarf so close to us is a reminder that these objects are common, and that not all of them are well understood. The study of RS Ophiuchi, then, is not just about one system. It is about understanding the pathway to the most important class of stellar explosion in cosmology. It is about knowing whether the standard candle is truly standard. It is about mapping the risks, however small, that our local galactic neighborhood contains. And it is about confronting a fundamental truth of astronomy. The universe operates on timescales that dwarf our comprehension, but the processes at work are relentless, and they do not pause for our convenience. RS Ophiuchi has erupted 7 times in a little over a century. It will almost certainly erupt again, probably within the next decade or two. When it does, astronomers around the world will mobilize within hours, pointing every available instrument at the constellation Ophiuchus. They will measure the ejector velocity, the ejected mass, the X-ray evolution, the gamma-ray emission. They will refine their estimates of the white dwarf's mass. They will update their models of the accretion rate and the retention fraction. And they will recalculate, once again, how close this system is to the edge. Each eruption brings a new set of answers. Each eruption also brings a new set of questions. And each eruption, whether we know it yet or not, may be bringing the system one step closer to its final act. We are, in a very real sense, witnesses to a process of cosmic construction. The white dwarf in RS Ophiuchi is being built, layer by hydrogen layer, into a bomb. The red giant, unwitting and indifferent, provides the raw material. Gravity provides the compression. Quantum mechanics provides the degenerate surface that prevents the thermostat from working, and the Chandrasekhar limit provides the threshold. Each component is passive. None of them intends anything. But together they form a mechanism as precise and as inevitable as any engineered device. The only variable is the timeline. If you were to drive a car at highway speed, roughly 100 kilometers per hour, toward RS Ophiuchi, the trip would take approximately 54 billion years. That is roughly 4 times the current age of the universe. RS Ophiuchi is far away by any human standard, but light, traveling at 300,000 kilometers per second, covers the distance in 5,000 years. The photons reaching our telescopes tonight left RS Ophiuchi when the earliest Egyptian pharaohs were building the first pyramids. When we observe an eruption, we are seeing events that happened 5 millennia ago. If the white dwarf crossed the Chandrasekhar limit and detonated in a Type Ia supernova at this very moment, we would not know for 5,000 years. The light would travel silently through the interstellar medium, crossing the voids between stars, threading through dust clouds and nebulae, until it arrived at Earth, where a future civilization would look up and see a new star blazing in the Serpent Bearer's constellation. It may have already happened. We would have no way of knowing. The universe does not send advance notices. It does not issue warnings in languages we understand. The light from RS Ophiuchi arrives at the speed of light, the fastest speed anything can travel, and it carries messages that are already 5,000 years old when we receive them. If the final eruption happened yesterday, by the standards of the system, we will learn about it in the year 7026, by our current calendar. This delay is not a safety margin. It is simply the consequence of living in a universe governed by the finite speed of light. We observe the past, we live in the present, and the future of RS Ophiuchi is already being written 5,000 light-years away in a language of gravity, pressure, and nuclear fire. What keeps astronomers watching, year after year, eruption after eruption, is not just scientific curiosity. It is a sense of responsibility. RS Ophiuchi is one of a handful of systems where the path to a Type Ia supernova can be studied in real time. The data gathered from this single binary star system informs our understanding of a phenomenon that shapes the large-scale structure of the universe itself. If we misunderstand the mechanism, we misunderstand the cosmos. The stakes could not be higher, and the system does not rest. Even now, between eruptions, the white dwarf is accreting. The hydrogen is piling up. The temperature at the base of the fuel layer is rising. The next eruption is being assembled, silently and invisibly, in the quiet depths of space. But here's what makes this truly terrifying. The question of whether RS Ophiuchi will one day produce a Type Ia supernova has been approached from multiple angles over the past several decades. Each approach offers insight, each approach has limitations, and each approach reveals a different facet of a problem that remains despite enormous effort unsolved. To understand where we stand, we need to walk through the major lines of investigation and examine what each one has found. The first and most direct approach is to measure the mass of the white dwarf. If we knew the mass precisely, we could calculate how far it sits from the Chandrasekhar limit and, combined with the accretion rate and retention fraction, estimate how long it would take to reach the threshold. In principle, this is straightforward. In practice, it is extraordinarily difficult. The mass of a star in a binary system can be determined from the orbital dynamics, specifically from the orbital period, the radial velocities of the two stars, and the inclination of the orbital plane relative to our line of sight. The orbital period of RS Ophiuchi is well established at approximately 456 days. The radial velocities of the red giant have been measured through Doppler shifts in its spectral lines, but the radial velocity of the white dwarf is much harder to measure because the white dwarf itself is faint and its spectral features are overwhelmed by the bright accretion disk and the red giant's light. Various research teams have attempted to constrain the white dwarf mass using different techniques. Some have used the dynamics of the nova ejector, arguing that the velocity and mass of the ejected material can be related to the mass and radius of the white dwarf through theoretical models of nova eruptions. Others have used the supersoft X-ray phase, which provides information about the ongoing nuclear burning on the white dwarf's surface after the eruption. The duration and luminosity of this phase are sensitive to the white dwarf's mass, because a more massive white dwarf has a higher surface gravity, which leads to more efficient burning and a shorter supersoft phase. Still others have used the orbital dynamics of the binary system, combined with assumptions about the red giant's properties, to derive the mass ratio and individual masses. The results have been broadly consistent but not precise. Most analyses place the white dwarf mass between 1.2 and 1.4 solar masses, with a best estimate around 1.3 to 1.35 solar masses. The uncertainty is on the order of 0.1 to 0.2 solar masses, which is large enough to matter. A white dwarf at 1.2 solar masses needs to gain 0.24 solar masses to reach the Chandrasekhar limit, a process that could take hundreds of millions of years. A white dwarf at 1.35 solar masses needs to gain only 0.09 solar masses, which could happen in tens of millions of years or less, depending on the retention efficiency. The difference between these two scenarios is the difference between a Type Ia supernova in the geologically near future and one that may never happen because the red giant runs out of mass to donate first. But here's the problem. The mass measurement uncertainty is not the only source of ambiguity. Even if we knew the white dwarf's mass exactly, we would still need to know the net mass retention rate per eruption cycle, and this is arguably even harder to determine. The second major approach to the RS Ophiuchi problem is to measure the ejected mass from each eruption and compare it to the total accreted mass between eruptions. If the ejected mass is less than the accreted mass, the white dwarf is gaining. If it is more, the white dwarf is losing. This sounds simple, but measuring the ejected mass of a nova is notoriously difficult. The ejected material is hot, fast, and mixed with the pre-existing stellar wind of the red giant. Distinguishing ejector from wind material requires careful spectroscopic analysis. The mass can be estimated from the density and velocity of the ejector, but these quantities depend on assumptions about the geometry, the filling factor, and the composition of the expanding shell. Early estimates of the ejected mass from RS Ophiuchi eruptions were highly uncertain, ranging from 100 millionth to 1/10 millionth of a solar mass. More recent analyses, particularly of the 2006 and 2021 eruptions, have converged on values toward the lower end of this range. The math is striking. If the white dwarf accretes roughly 1 to 2 millionths of a solar mass between eruptions and ejects roughly 100 millionth to 1/10 millionth of a solar mass during each eruption, then the retention is overwhelmingly positive. The white dwarf is keeping the vast majority of the accreted material. Even accounting for material dredged up from the core, the net balance appears to favor mass growth, but not all researchers agree. Some models of the nova eruption predict that the amount of core material dredged up and ejected can be comparable to, or even greater than the amount of accreted hydrogen retained. If the white dwarf is eroding its own carbon-oxygen core during each eruption, the net mass change could be negative even if the amount of hydrogen retained is positive. The mixing of core material into the ejector has been observed spectroscopically in some novae, with enhanced abundances of carbon, oxygen, and neon detected in the expanding shell. However, the degree of mixing in RS Ophiuchi appears to be less extreme than in some other novae, possibly because the very high mass of the white dwarf leads to a shallower and more efficient thermonuclear runaway that does not penetrate as deeply into the core. The third approach to the problem involves theoretical modeling of the accretion and eruption process. Over the past 4 decades, a series of increasingly sophisticated computer simulations have been developed to model the evolution of accreting white dwarfs. These simulations track the buildup of hydrogen on the white dwarf's surface, the onset of thermonuclear runaway, the propagation of the burning front, the ejection of mass, and the subsequent recovery. By running these simulations over many eruption cycles, researchers can predict the long-term evolution of the white dwarf's mass. The results depend sensitively on the input parameters, particularly the white dwarf mass, the accretion rate, and the metallicity of the accreted material. For parameters representative of RS Ophiuchi, most modern simulations predict positive mass growth, though the rate varies. Some models predict that the white dwarf will reach the Chandrasekhar limit within a few million years. Others predict it will take tens of millions of years, and some models, using slightly different assumptions about the convective mixing during the eruption, predict that the growth is so slow as to be negligible, with the red giant running out of mass to donate before the white dwarf reaches the limit. The disparity among models reflects genuine uncertainties in the physics of convection, turbulence, and nuclear burning in degenerate material. These are hard problems, and they are not yet fully solved. The fourth approach involves studying the population of type Ia supernova themselves and working backward to constrain the progenitor systems. Type Ia supernovae are observed in galaxies throughout the universe, at rates that depend on the age and star formation history of the host galaxy. By analyzing the delay time distribution, the distribution of time intervals between the formation of a stellar population and the occurrence of type Ia supernovae within it, astronomers can infer what kinds of progenitor systems are responsible. If most type Ia supernovae come from systems like RS Ophiuchi, where a white dwarf accretes from a companion, the delay time should cluster around a few 100 million to a few billion years, reflecting the time needed for the red giant to evolve and the white dwarf to accrete enough mass. If most come from the mergers of 2 white dwarfs, the double degenerate channel, the delay times should span a wider range, extending to many billions of years. Observational studies of the delay time distribution have yielded mixed results. Some analyses favor a prompt component, with a significant fraction of type Ia supernovae occurring within a few 100 million years of star formation, which is consistent with the single degenerate channel that RS Ophiuchi represents. Others find that the distribution is dominated by a delayed component extending to many billions of years, which favors the double degenerate merger scenario. The current consensus, such as it is, suggests that both channels contribute, but their relative importance remains hotly debated. One piece of evidence that bears directly on this question comes from the search for surviving companion stars in the remnants of nearby Type Ia supernovae. If the single degenerate channel is responsible, the companion star, whether a red giant or a main sequence star, should survive the supernova and be visible within the expanding remnant. Astronomers have searched for such surviving companions in several nearby Type Ia supernova remnants, including Tycho's supernova remnant and SN 1011, the remnant of a supernova observed by Chinese astronomers in the year 1011. The results have been inconclusive. Some studies have claimed to identify candidate companion stars. Others have found no convincing evidence. The absence of a clear surviving companion in these remnants has been used to argue against the single degenerate channel, but the argument is not definitive because the companion could have been disrupted or stripped of its outer layers by the supernova blast, making it difficult to identify. A fifth and final approach to the RS Ophiuchi problem involves direct comparison with other recurrent nova and with systems that have already produced Type Ia supernova. The recurrent nova U Scorpii mentioned earlier is in many ways a sibling of RS Ophiuchi. Its white dwarf is also very massive, its eruptions are also frequent, and its accretion rate is also high. But U Scorpii has a different type of companion, a slightly evolved main sequence star rather than a red giant, and its eruptions have different characteristics. By comparing the two systems, astronomers can test whether the mass growth rates predicted by models are consistent with the observed properties of both. Beyond our own galaxy, the recurrent nova M31N 2008-12A, discovered in the Andromeda Galaxy, has provided a remarkable case study. This system erupted in 2008 and again in 2012, with an interval of only 4 years, making it the fastest known recurrent nova. Its extremely short recurrence time suggests an extraordinarily massive white dwarf with a very high accretion rate, and it has been suggested as one of the most compelling progenitor candidates for a future Type Ia supernova in Andromeda. The numbers are striking when you lay them side by side. RS Ophiuchi erupts every 15 to 20 years, with a white dwarf mass near 1.35 solar masses. U Scorpii erupts every 10 to 12 years, with a possibly higher mass. The Andromeda recurrent nova erupts every 4 years. If the pattern holds, shorter recurrence times indicate more massive white dwarfs, higher accretion rates, and a closer approach to the Chandrasekhar limit. These systems form a sequence, a spectrum of objects at different stages along the same evolutionary path. RS Ophiuchi may be midway along that path. The Andromeda nova may be closer to the end, or the path may branch, and some systems may reach the limit while others stall. What emerges from all 5 approaches is not a definitive answer, but a probability landscape. The evidence leans toward mass growth for the white dwarf in RS Ophiuchi. Most measurements of the white dwarf mass place it near the Chandrasekhar limit. Most estimates of the ejected mass suggest it is less than the accreted mass. Most theoretical models predict positive net retention, and the population studies of Type Ia supernovae leave room for the single degenerate channel to contribute, perhaps significantly. But none of these lines of evidence is conclusive on its own. The mass measurements have uncertainties. The ejected mass estimates depend on modeling assumptions. The theoretical simulations are sensitive to poorly constrained physics, and the population studies cannot yet distinguish which specific systems will produce Type Ia supernovae and which will not. The situation is analogous to predicting whether a specific volcano will erupt in the next century. We can measure the seismic activity, we can monitor the gas emissions, we can track the deformation of the surface. All of these indicators may point toward an eruption, but the exact timing remains unpredictable. The system is complex, the variables are many, and the triggers are poorly understood. What we can say with confidence is that the indicators are there. The system is active. The trajectory, as far as we can measure it, points in one direction, and the consequences, if the trajectory reaches its endpoint, are enormous. Then something happened that changed everything. In August of 2021, RS Ophiuchi erupted for the 7th time in recorded history, and for the first time ever, a nova was detected in very high energy gamma rays. The HESS telescope array in Namibia followed by other ground-based and space-based gamma-ray instruments, captured photons with energies exceeding 100 billion electron volts streaming from the system. These gamma rays were produced by protons accelerated to nearly the speed of light in the shock wave created by the nova blast. The protons collided with the dense wind of the red giant, producing pions that decayed into gamma-ray photons. This process, called hadronic acceleration, had been theorized for years but never observed in a nova. Its detection in RS Ophiuchi opened a new window onto the physics of these systems and provided fresh constraints on the density, velocity, and energy budget of the eruption. The 2021 observations also confirmed, with better precision than ever, that the ejected mass was low and the white dwarf was behaving consistently with previous eruptions. The system was not winding down, it was not losing energy, it was continuing on its trajectory, cycle after cycle, eruption after eruption, with a regularity that bordered on mechanical. And this is where the answer becomes deeply unsettling, because the more data we gather, the more observations we make, and the more models we run, the more the evidence converges on a single conclusion. The white dwarf in RS Ophiuchi is growing. It is approaching the Chandrasekhar limit, and unless something changes, something we have not yet observed or understood, it will reach that limit. The question is not whether, but when. But let us not rush past the details of these approaches, because each one reveals subtleties that matter. Consider the theoretical modeling in more depth. The computer codes used to simulate nova eruptions are among the most complex in all of stellar astrophysics. They must track nuclear reactions involving dozens of isotopes simultaneously. They must model the convective transport of energy and material in a thin shell sitting on top of a degenerate surface. They must account for the transition from subsonic deflagration to supersonic detonation, if such a transition occurs. And they must do all of this in 3 dimensions, because the burning is not symmetric. Plumes of burning material rise from the base of the hydrogen layer, break through the surface, and interact with the surrounding gas in chaotic, turbulent patterns. The earliest nova models, developed in the 1970s and 1980s by researchers like Sumner Starfield at Arizona State University, James Truran at the University of Chicago, and Warren Sparks, were one-dimensional. They treated the nova as a spherically symmetric event, which simplified the calculations enormously, but missed much of the real physics. These models were the first to demonstrate that thermonuclear runaway on a white dwarf surface could produce the energy and timescales observed in nova eruptions. They established the basic framework that is still used today, but they also predicted higher ejected masses and more core dredge-up than is now thought to occur in systems like RS Ophiuchi. In the 1990s and 2000s, multidimensional models began to emerge. Researchers used 2-dimensional and eventually 3-dimensional hydrodynamic codes to simulate the convective burning on the white dwarf surface. These models revealed that the burning is highly turbulent and asymmetric. Hot plumes rise rapidly from the burning layer, carrying nuclear-processed material upward while cooler material sinks down to be burned. The mixing between accreted material and core material is driven by these convective instabilities, and the extent of mixing depends on the details of the turbulence, which in turn depends on the resolution of the simulation. Higher resolution simulations tend to find less mixing and lower ejected masses, which is encouraging for the mass growth scenario. A key advance came in the 2000s and 2010s, when several groups developed models specifically tailored to recurrent novae with very massive white dwarfs. These models found that when the white dwarf mass exceeds about 1.2 solar masses, the nova eruption becomes qualitatively different from classical novae on lower mass white dwarfs. The hydrogen layer is thinner at ignition, the thermonuclear runaway is faster and more violent. But the total energy released is lower because there is less fuel, and critically, the amount of core material dredged up is smaller. The explosion is, in a sense, more efficient. It burns the fuel quickly, ejects a small amount of mass at high velocity, and leaves the rest behind. This is exactly what observations of RS Ophiuchi show. The ejecta are fast but sparse. The eruption is bright but brief, and the white dwarf recovers quickly, resuming accretion within weeks to months. These results have been confirmed by multiple independent research groups using different codes and different numerical techniques. While the quantitative predictions vary, the qualitative picture is robust. Massive white dwarfs in recurrent nova systems retain a significant fraction of the accreted mass through each eruption cycle. The retention fraction depends on the specific parameters, but estimates for RS Ophiuchi-like systems range from 20% to as high as 60 or 70%. Even at the conservative end, 20% retention over thousands of eruption cycles adds up to a substantial mass increase. Now let us consider an angle that is less often discussed but equally important: the chemical evolution of the white dwarf's surface layers. Each nova eruption processes hydrogen into helium through the CNO cycle, but not all of the processed helium is ejected. Some of it remains on the white dwarf's surface, accumulating over many eruption cycles. Over time, this helium layer grows, and helium, like hydrogen, can undergo thermonuclear ignition if it reaches sufficient temperature and density. Helium burning on a white dwarf surface is even more explosive than hydrogen burning, because helium ignites at higher temperatures and releases more energy per unit mass. If a sufficiently thick helium layer accumulates, it can detonate in what is called a helium shell flash. This helium flash can, in some models, trigger the detonation of the underlying carbon-oxygen core, even if the total mass of the white dwarf has not quite reached the Chandrasekhar limit. This is the sub-Chandrasekhar detonation scenario, sometimes called the double detonation model. In the double detonation model, the helium shell detonation produces a converging shock wave that compresses the carbon-oxygen core and triggers a secondary detonation. The result is a complete disruption of the white dwarf, just as in the standard Chandrasekhar mass model, but occurring at a slightly lower total mass. Some theoretical studies suggest that a white dwarf as light as 1 solar mass could be detonated through this mechanism if the helium layer is massive enough. For a white dwarf near 1.3 solar masses, like the one in RS Ophiuchi, the required helium layer is relatively thin, perhaps 1 to 5/100ths of a solar mass. This is a chilling possibility. It means that the white dwarf in RS Ophiuchi may not need to reach the full Chandrasekhar limit of 1.44 solar masses to undergo a catastrophic detonation. It may only need to accumulate enough helium between hydrogen eruptions to trigger a helium shell flash. And because helium accumulates more slowly than hydrogen, the timescale for this process is longer, but it is another pathway to the same endpoint. Another mechanism pointing in the same direction. Not all astronomers accept the double detonation scenario for RS Ophiuchi. The main objection is that the frequent hydrogen eruptions may prevent a thick helium layer from accumulating. Each nova eruption heats and disrupts the surface, potentially mixing the helium layer with the freshly accreted hydrogen and preventing the helium from reaching ignition conditions. The interplay between hydrogen novae and helium accumulation is complex and not fully resolved, but the possibility remains on the table. There is also the question of what happens to the system between eruptions. The accretion process is not perfectly steady. The red giant's stellar wind varies in intensity over time, driven by pulsations and convective motions in the giant's atmosphere. The accretion rate onto the white dwarf fluctuates accordingly. During periods of enhanced mass transfer, the accretion disk brightens and the system shows increased optical and X-ray activity. During quiet periods, the system fades. These fluctuations introduce noise into the eruption timing, which is why the intervals between observed eruptions are not perfectly regular. Observations of RS Ophiuchi between eruptions have revealed a complex phenomenology. In the optical band, the system shows ellipsoidal variations, brightness changes caused by the changing aspect of the tidally distorted red giant as it orbits the white dwarf. These variations have a period of about 456 days, matching the orbital period. In the near-infrared, the red giant dominates the light, and its spectral features reveal that it is a late-type red giant, probably of spectral type M0 to M2, with a surface temperature of roughly 3,500 to 4,000 degrees Celsius. In the ultraviolet and X-ray bands, the accretion disk and the boundary layer between the disk and the white dwarf produce detectable emission. The most telling observations of the quiescent state come from high-resolution optical spectroscopy, which reveals the complex gas dynamics of the binary system. Emission lines from the accretion disk are visible, broadened by the rapid rotation of the disk material. Absorption features from the red giant's atmosphere provide information about its chemical composition and surface gravity, and occasionally, narrow emission features from the region between the two stars reveal the geometry and velocity of the mass transfer stream. What emerges from this comprehensive body of work, spanning more than a century of observations and decades of theoretical modeling, is a picture that is incomplete but increasingly coherent. RS Ophiuchi is a system in which a massive white dwarf, close to the Chandrasekhar limit, is accreting material from a red giant companion at a rate sufficient to trigger thermonuclear eruptions every 15 to 20 years. Each eruption ejects a small amount of mass but retains a larger amount. The white dwarf is growing. Multiple independent lines of evidence support this conclusion. The uncertainties are real. The measurement errors are significant. The theoretical models disagree on the quantitative details, but the direction of the evidence is clear. And when multiple independent approaches, using different data, different methods, and different assumptions, all point in the same direction, the conclusion carries weight, not certainty. But wait, let us now return to the broader cosmological context, because the significance of RS Ophiuchi extends far beyond one binary star system. Type Ia supernovae are not merely spectacular explosions. They are the foundation of modern cosmological distance measurement. Without them, we would not know the expansion rate of the universe. We would not know that the expansion is accelerating. We would not know about dark energy. The entire framework of precision cosmology, the science of measuring the age, size, and fate of the universe, rests on the assumption that Type Ia supernovae are reliable standard candles. And that assumption, in turn, rests on our understanding of the progenitor systems. The standard candle argument works like this. If all Type Ia supernovae reach the same peak luminosity, then by measuring how bright one appears from Earth, we can calculate how far away it is. Fainter means farther. Brighter means closer. This is the inverse square law of light, one of the simplest and most powerful tools in all of physics. A candle held at twice the distance appears 4 times dimmer. At 10 times the distance, 100 times dimmer. By calibrating the true brightness of Type Ia supernovae using nearby examples whose distances are known by other methods, astronomers can use them as rulers to measure distances across billions of light years. In 1998, 2 teams of astronomers, the Supernova Cosmology Project led by Sol Perlmutter and the HiZ Supernova Search Team led by Brian Schmidt and Adam Rees, announced a discovery that shook the foundations of physics. By measuring the distances and redshifts of dozens of distant Type Ia supernovae, they found that the supernovae were dimmer than expected, not by much, but consistently. The implication was stunning. The universe was not just expanding, it was expanding faster and faster. Something was pushing the galaxies apart, working against the pull of gravity. That something became known as dark energy, and it accounts for roughly 68% of the total energy content of the universe. Perlmutter, Schmidt, and Reis shared the Nobel Prize in Physics in 2011 for this discovery. But here is the catch. The entire discovery depends on the assumption that Type Ia supernovae are standard candles. If they are not, if their peak brightness varies in ways we do not fully understand, then the distance measurements could be systematically wrong, and the evidence for dark energy could be weaker than we think, or stronger. The point is that uncertainty in the standard candle calibration translates directly into uncertainty in the fundamental properties of the universe. And this is where RS Ophiuchi becomes cosmologically important. If RS Ophiuchi is a genuine Type Ia supernova progenitor, then it represents the single degenerate channel, a white dwarf accreting from a companion star until it reaches the Chandrasekhar limit. In this channel, the explosion always occurs at the same total mass, which is why the peak brightness is expected to be uniform. But if most Type Ia supernovae actually come from the merger of 2 white dwarfs, the double degenerate channel, then the total mass at detonation can vary. 2 white dwarfs with combined masses of 1.5 solar masses will produce a different explosion than two with combined masses of 2.0 solar masses. The brightness may differ, the light curve shape may differ, the chemical composition of the ejector may differ, and the standard candle may not be as standard as assumed. Understanding which channel dominates and whether RS Ophiuchi is a genuine representative of the single degenerate pathway is therefore not just an academic exercise. It is a test of the reliability of our cosmic distance ladder. It is a test of the evidence for dark energy. It is, in the most fundamental sense, a test of our understanding of the universe. Current evidence suggests that both channels contribute to the type Ia supernova rate, but their relative contributions remain uncertain. Some estimates attribute 60 to 70% of type Ia supernovae to the double degenerate channel and 30 to 40% to the single degenerate channel. Others reverse these proportions. The truth is probably more nuanced, with the relative importance varying depending on the age and metallicity of the stellar population. In young stellar populations, where massive red giants are common, the single degenerate channel may dominate. In old populations, where red giants have evolved away and only white dwarf pairs remain, the double degenerate channel may take over. RS Ophiuchi, as a member of the disk population of the Milky Way with a moderately old stellar companion, may represent a transitional case. It is neither the youngest nor the oldest type of progenitor system. It is simply the one we can study most thoroughly, because it is nearby, it erupts frequently, and it has been observed for more than a century. Every time RS Ophiuchi erupts, it gives us another data point, another constraint, another piece of the puzzle, and every piece brings us closer to answering the question that underlies all of modern cosmology. How well do we really understand the standard candle? There is one more observation that deserves mention in this context, because it illustrates the subtle interplay between different types of evidence. In 2012, a team of astronomers published a study of the X-ray emission from RS Ophiuchi during its quiescent phase between eruptions. Using data from the XMM Newton Space Telescope, they detected a faint but persistent X-ray source at the position of RS Ophiuchi, consistent with emission from the boundary layer of the accretion disk. By modeling this emission, they were able to estimate the accretion rate during quiescence at roughly 1 to 2 10-millionths of a solar mass per year. This was broadly consistent with the accretion rate required to produce eruptions every 15 to 20 years, which provided an independent check on the system parameters derived from the eruptions themselves. More importantly, the quiescent X-ray observations showed no evidence that the accretion rate was declining over time. The system was fueling at a steady rate. The red giant was continuing to provide material. The assembly of the next eruption was proceeding on schedule, and by extension, the long-term mass growth of the white dwarf was continuing uninterrupted. The accumulated weight of evidence, from the mass measurements, the ejected mass estimates, the theoretical models, the population studies, the chemical evolution considerations, the gamma-ray observations, and the quiescent X-ray monitoring all converges on the same broad conclusion. RS Ophiuchi is a system in which the conditions for a future type Ia supernova are being actively assembled. The white dwarf is massive, the accretion is ongoing, the retention is positive, the trajectory is clear. What remains unknown is the timeline, and it is the timeline that separates a fascinating scientific puzzle from an existential concern. Tens of millions of years is a long time, long enough for continents to shift, for species to evolve and go extinct, for entire civilizations to rise and fall thousands of times over. The chances that RS Ophiuchi will detonate in any given human lifetime are vanishingly small, but the chances are not zero, and in a universe governed by probability and vast timescales, even small probabilities become certainties given enough time. The next eruption of RS Ophiuchi will likely occur sometime in the mid-2030s, based on the average interval since the last eruption in 2021. When it comes, it will be observed by the most powerful suite of telescopes ever assembled, including the James Webb Space Telescope, the Vera-C, Rubin Observatory, and a new generation of gamma-ray and neutrino detectors. Each observation will refine our understanding, Each observation will bring us one step closer to knowing whether this system is truly building toward the ultimate explosion. And until then, the white dwarf waits. It accretes, it heats, it builds, silently, patiently, in the dark. Consider, as a final thought on the investigative approaches, the remarkable precision that modern astronomy has achieved and the remarkable gaps that remain. We can measure the distance to RS Ophiuchi to within a few hundred light-years using parallax measurements from the Gaia satellite. We can determine the orbital period to within a fraction of a day. We can measure the ejector velocity to within a few percent using Doppler spectroscopy. We can detect gamma-ray photons with energies exceeding 100 billion electron volts, individual packets of energy so powerful that each one carries the kinetic energy of a well-struck tennis ball concentrated into a single subatomic particle. And yet, we cannot determine whether the white dwarf is at 1.2 or 1.4 solar masses. We cannot definitively say whether it gains or loses mass per eruption cycle. We cannot predict within a factor of 10 when, or even whether, it will reach the Chandrasekhar limit. The system is at once one of the best studied objects in stellar astrophysics and one of the most uncertain. This paradox, this coexistence of extraordinary knowledge and fundamental ignorance, is one of the defining features of modern astronomy. We see farther and more clearly than ever before, and what we see reminds us how much we still do not understand. RS Ophiuchi sits at the intersection of the known and the unknown, the measured and the conjectured. It is a system where the physics is clear but the outcome is not, where the mechanism is understood but the endpoint is uncertain, where every eruption brings new answers and deeper questions, and where the ultimate resolution, whether it comes in 1,000,000 years or 1 billion, will be written not by human hands but by the implacable arithmetic of gravity and nuclear physics. What makes the story of RS Ophiuchi so profoundly unsettling is not the explosion itself. Stars explode. The universe is violent. We have known this for centuries. What is unsettling is the realization that the tools we use to measure the cosmos, the very instruments of understanding that allow us to comprehend the age, size, and fate of the universe, are built on systems that we do not fully understand. RS Ophiuchi is not just a potential supernova. It is a mirror held up to our ignorance. This is not science fiction. This is a real star system, observed by real telescopes, studied by real scientists, producing real data that challenges our most fundamental assumptions about the universe. And the challenge is not abstract. It has consequences. The discovery of dark energy in 1998 was built on the assumption that Type Ia supernovae are standard candles, that their peak brightness is uniform, predictable, and well calibrated. That assumption has been tested and refined over the past quarter century. The original observations by the Supernova Cosmology Project and the HISE Supernova Search Team have been confirmed by hundreds of subsequent observations. The evidence for dark energy is now considered very strong, but strong is not the same as certain, and the residual uncertainty comes, in large part, from the progenitor problem. If we do not know what systems produce Type Ia supernovae, we do not fully know what controls their brightness. And if we do not fully know what controls their brightness, our distance measurements have a systematic error that we cannot yet quantify. This error might be small, it might be negligible, but it might not. And in a field where the measured acceleration of the expansion is itself a small effect, requiring precise measurements to distinguish from a decelerating universe, even a modest systematic error could be significant. Let that sink in. The evidence for dark energy, the mysterious force that constitutes 68% of the total energy of the universe and determines its ultimate fate, depends in part on our understanding of binary star systems like RS Ophiuchi. A small, violent star system in the constellation of the Serpent Bearer is connected by a chain of physics and observation to the largest question in all of science. What is the universe made of, and what will happen to it? To make this connection concrete, consider what happens if the standard candle is not perfectly standard. Suppose that Type E supernovae from the single degenerate channel, white dwarfs accreting from companions like RS Ophiuchi, have a slightly different peak brightness than Type Ia supernovae from the double degenerate channel, white dwarf mergers. Suppose the difference is only 5%. That is, within the current measurement uncertainty. 5% does not sound like much, but at cosmological distances, a 5% error in brightness translates to a 2.5% error in distance, and a 2.5% error in distance, compounded across a sample of supernovae at different redshifts, could shift the inferred expansion history of the universe by an amount that changes our understanding of dark energy. Is dark energy constant over time, a true cosmological constant, as Einstein proposed in 1917? Or does it change, growing stronger or weaker as the universe ages? The answer depends on measuring the expansion rate at different epochs with extreme precision, and that precision depends on the standard candle, which depends on the progenitor, which depends on systems like RS Ophiuchi. The chain is long but unbroken, from the surface of a white dwarf to the fate of the universe, from a thermonuclear runaway in the constellation Ophiuchus to the question of whether the cosmos will expand forever or eventually reverse course, from a small flickering point of light to the deepest mystery in physics. Let that sink in. There is another dimension to the deeper truth of RS Ophiuchi, one that extends beyond cosmology into the realm of existential risk, however small. We have established that a Type Ia supernova at 5,000 light-years would not directly harm Earth. The radiation dose would be trivial at that distance. The cosmic rays would be absorbed by the heliosphere and the magnetosphere. The visible light, while spectacular, would be harmless. But the implications extend further. A Type Ia supernova at 5,000 light-years would be the closest observed in the modern era of astronomy. It would saturate every instrument pointed at it. The Hubble Space Telescope, the James Webb Space Telescope, and every ground-based observatory would be temporarily blinded if they looked directly at the source. The burst of neutrinos, though far less intense than from a core collapse supernova, might be detectable by large neutrino observatories like IceCube in Antarctica or Super Kamiokande in Japan, providing a fundamentally new probe of the explosion mechanism. The gravitational waves produced by the rapid thermonuclear detonation, though extremely faint, might be detectable by future space-based gravitational wave observatories like LISA. The scientific return would be incalculable. But there is a deeper implication. A Type Ia supernova at that distance would force us to confront the reality that our local galactic neighborhood is not as safe as we assume. The Milky Way produces perhaps 1 or 2 Type Ia supernovae per millennium. That rate, spread over the entire volume of the galaxy, makes the probability of a nearby event very low in any given century, but low is not zero, and over millions of years, the probability accumulates. The fossil record contains possible evidence of nearby supernova events influencing Earth's climate and biosphere. The radioactive isotope iron-60, which is produced in supernova explosions and has a half-life of about 2.6 million years, has been detected in deep-sea sediments and on the ocean floor, suggesting that one or more supernovae occurred within a few hundred light-years of Earth within the past few million years. These were probably core collapse supernovae, not Type Ia events, but the principle is the same. The galaxy is not static. Stars explode, and some of them explode nearby. RS Ophiuchi reminds us that the mechanisms producing these explosions are not theoretical abstractions. They are ongoing physical processes, observable and measurable, unfolding on timescales that overlap with human civilization. We cannot prevent a Type Ia supernova. We cannot redirect a white dwarf. We cannot negotiate with gravity. All we can do is watch, measure, model, and understand. And understanding is not nothing. Understanding is in fact everything. It is the only tool we have. There is a philosophical dimension to this realization that is worth sitting with for a moment. The universe, as far as we can tell, is not designed for our benefit. It operates according to laws that are indifferent to our existence. Gravity does not care about civilizations. Nuclear physics does not pause for sentience. The Chandrasekhar limit is a number, derivable from first principles, that applies regardless of whether anyone is around to calculate it. The white dwarf in RS Ophiuchi does not know that it is being observed. The red giant does not know that it is feeding a potential bomb. The system operates in complete indifference to meaning, and yet we assign meaning to it, We name the constellation, we track the eruptions, we build telescopes to observe the explosions, we develop theories to explain the physics. We connect the behavior of one binary star system to the large-scale structure of the universe. This act of connection, of drawing meaning from indifferent processes, is perhaps the most remarkable thing about human consciousness. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence. We are the universe observing itself, through instruments we built, from a planet we were not guaranteed, in a brief moment of awareness that the cosmos did not arrange. RS Ophiuchi will outlast us. Whether it detonates in a Type Ia supernova or continues cycling as a recurrent nova for another billion years, it will be there long after every human who has ever studied it is gone. The photons from its next eruption will travel through space at 300,000 kilometers per second, indifferent to whether anyone is waiting to receive them. And if, in some distant future, the final eruption comes, the one that crosses the Chandrasekhar limit and obliterates the white dwarf entirely, the flash of light will propagate outward at the speed of light, a spherical shell of photons expanding through the galaxy, washing over star systems and planets and dust clouds and void, carrying the signature of one of the most violent events in nature. And somewhere, perhaps, an intelligence will notice, or perhaps not. The universe does not require witnesses, but we are witnesses. We are here now watching, and what we see when we look at RS Ophiuchi is a system that connects the smallest scales of nuclear physics to the largest scales of cosmology, a system where the quantum mechanical pressure of individual electrons determines the fate of a star, and the fate of that star determines how we measure the cosmos. A system where a calculation performed by a 20-year-old physicist on a steamship in 1930 echoes across 93 billion light-years of observable universe. The deeper truth of RS Ophiuchi is not that it might explode. The deeper truth is that it reveals how interconnected our universe is, how a single number, 1.44 solar masses, connects electron physics to stellar death, to galactic evolution, to cosmological measurement, how a single binary star system, flickering in the constellation of the Serpent Bearer, can illuminate the fundamental nature of the cosmos, and how our understanding of that cosmos, our map of reality, is only as good as our understanding of the systems that produced the data we use to draw it. We are living in a universe measured by the deaths of stars. The distances are calibrated by explosions. The age is determined by the brightness of thermonuclear detonations billions of light years away. And the reliability of those measurements depends on our understanding of systems like RS Ophiuchi, systems we are still learning to comprehend, systems that erupt without warning and reshape our theories with each new observation. The map is not the territory, but in cosmology, the map is all we have, and the map is drawn in starlight from dying suns. But the implications extend further still, into territory that few discussions of RS Ophiuchi explore. Consider the element synthesis. When a Type Ia supernova detonates, it does not merely release energy, it forges matter. The thermonuclear burning that consumes the carbon and oxygen core produces vast quantities of intermediate mass and iron peak elements. A single Type Ia supernova produces roughly 0.6 to 0.8 solar masses of radioactive nickel-56, which decays to cobalt-56 and then to iron-56 over a period of weeks to months. This decay chain is what powers the supernova's light curve, keeping it visible for months after the initial explosion. The iron produced by Type Ia supernovae is the dominant source of iron in the universe. Every iron atom in your blood, every iron atom in every piece of steel ever forged, every iron atom in the core of the Earth, was once inside a white dwarf that crossed the Chandrasekhar limit and detonated. Or it was produced in a core collapse supernova, which also produces iron, but in different proportions and by a different mechanism. The relative contributions of Type Ia and core collapse supernovae to the total iron budget of the galaxy depend on their respective rates and yields, both of which are subjects of ongoing research. But the connection is direct and profound. The material world we inhabit, the atoms in our bodies, the metals in our technology, the minerals in our planet, were synthesized in stellar explosions. and a significant fraction of those explosions were Type Ia supernovae, detonations of white dwarfs that may have resembled the white dwarf in RS Ophiuchi. We are not merely observers of these events, we are products of them. The iron in your hemoglobin was forged in an explosion that obliterated a star. The calcium in your bones was built in the nuclear fires of a dying sun. The silicon in the glass of your screen was assembled in the burning layers of a massive star or in the thermonuclear detonation of a white dwarf. This is not metaphor, this is chemistry. This is nuclear physics. This is the literal truth of our material origin. We are stardust, as Carl Sagan famously said. But more specifically, we are supernova ash. We are the residue of the most violent events in the cosmos, reassembled by gravity and chemistry into forms complex enough to contemplate our own origins. RS Ophiuchi is, in this sense, a factory that has not yet completed its most important production run. The nova eruptions it produces now are small and temporary. They expel material into the surrounding medium, enriching the interstellar gas with processed elements. But the real contribution, the contribution that will reshape the chemical landscape of its local environment, will come when the Type Ia supernova finally occurs, if it occurs. When the white dwarf detonates, it will scatter roughly 1.4 solar masses of newly synthesized elements into space. That material will mix with the interstellar medium, be swept up into molecular clouds, and eventually be incorporated into new stars and new planets. Some of those planets may develop conditions suitable for chemistry, and some of that chemistry may, over billions of years, become complex enough to be called life. And that life, if it ever looks up at the stars and wonders where it came from, will trace its origin, in part, to the death of a white dwarf that once was called RS Ophiuchi. The cycle is beautiful in its symmetry. Stars are born from the ashes of dead stars. The elements forged in one generation of explosions become the raw material for the next generation of worlds. And in rare, extraordinary cases, those worlds produce beings who can comprehend the cycle, who can look at a flickering point of light in the constellation Ophiuchus and understand, with rigorous mathematical precision, what it is, what it was, and what it may become. This comprehension is not guaranteed. It is not inevitable. It is an accident of evolution on a small rocky planet orbiting an unremarkable star in the outer suburbs of an ordinary spiral galaxy. But it is real, and it connects us, in a direct and unbroken chain of cause and effect, to the nuclear fires burning on the surface of a white dwarf 5,000 light-years away. There is something humbling about this connection. We are small. We are temporary. Our civilization has existed for less than 1,000th of 1% of the age of the universe. Our species has existed for less than 100th of 1%. The entire history of multicellular life on Earth fits into the last 10% of the planet's existence. And yet, within this tiny window, we have developed the capacity to observe, measure, and understand events occurring across billions of light years and billions of years. We have built instruments that can detect individual photons from explosions that happened when the universe was a fraction of its current age. We have developed theories that can predict, with remarkable accuracy, the behavior of matter under conditions that no laboratory on Earth can replicate. This capacity for understanding is, in a very real sense, the most extraordinary thing we know of in the entire universe. More extraordinary than black holes, more extraordinary than neutron stars, more extraordinary than dark energy. Because all of those phenomena are consequences of simple physical laws operating on passive matter. Understanding requires something more. It requires a system complex enough to model the universe internally, to build representations of reality, and to test those representations against observation. As far as we know, we are the only such system in existence, and our understanding of the cosmos, imperfect and incomplete as it is the universe's only window into itself. RS Ophiuchi does not care about this. The white dwarf will continue accreting whether or not anyone watches. The eruptions will come whether or not anyone records them. The Chandrasekhar limit will be reached or not, regardless of whether any civilization exists to calculate the probability. But the act of watching, of recording, of calculating, transforms the event from mere physics into something else, something that has meaning. Not inherent meaning, not cosmic meaning, human meaning. The meaning we create when we look at the universe and refuse to look away. And there is one final thread that deserves to be woven into this tapestry. The discovery of very high-energy gamma rays from RS Ophiuchi in 2021 did more than just add another wavelength to the multi-messenger picture of nova eruptions. It revealed that novae are sites of cosmic ray acceleration. Cosmic rays are charged particles, primarily protons, that travel through the galaxy at nearly the speed of light. They carry enormous energies, and their origin has been one of the longest-standing mysteries in astrophysics. For decades, supernova remnants have been considered the primary source of galactic cosmic rays. But the HEST detection showed that novae, too, can accelerate particles to very high energies. The shockwave produced by the nova eruption, slamming into the dense, red giant wind, creates conditions in which protons bounce back and forth across the shock front, gaining energy with each crossing in a process called diffusive shock acceleration or Fermi acceleration. The implications are significant. If recurrent novae like RS Ophiuchi produce cosmic rays with each eruption, and if there are dozens or hundreds of such systems in the Milky Way, then novae may contribute a measurable fraction of the total galactic cosmic ray flux. This is a new idea, one that arose directly from the RS Ophiuchi observations, and it connects yet another piece of the astrophysical puzzle to this single binary star system. Cosmic rays affect interstellar chemistry, ionize molecular clouds, and may influence the formation of new stars and planets. If novae are significant sources of cosmic rays, then the recurrent novae of the galaxy are not just potential supernova progenitors. They are active participants in the chemical and physical evolution of the interstellar medium, shaping the environment in which future stars and planets will form. The deeper truth, then, is not a single revelation. It is a web of connections. RS Ophiuchi connects to the Chandrasekhar limit, which connects to Type Ia supernovae, which connect to the cosmic distance ladder, which connects to dark energy, which connects to the fate of the universe. RS Ophiuchi connects to element synthesis, which connects to the composition of planets, which connects to the chemistry of life. RS Ophiuchi connects to cosmic ray acceleration, which connects to interstellar chemistry, which connects to star formation, which connects back, full circle, to the birth of new binary systems that may one day become recurrent novae themselves. It is all connected. The nova and the nebula, the white dwarf and the universe, the eruption and the evolution, the explosion and the existence. One system, one chain of physics, one unbroken line from the quantum mechanics of degenerate electrons to the large-scale geometry of space-time. And at the center of it all, a dead star that refuses to stay dead, a corpse that feeds, erupts, recovers, and feeds again. A system caught between annihilation and renewal, between the violence of nuclear fire and the patience of gravitational accretion. A system that has been doing this for longer than human civilization has existed, and will continue doing it long after we are gone, unless one day it crosses the line, and then it will stop, forever. The stopping will not be gradual, it will not be a fading, it will be an event of total and instantaneous finality. One moment, the white dwarf will be a dense, hot ball of carbon and oxygen, surrounded by a thin layer of accreted hydrogen and helium, orbiting a red giant companion in a slow, predictable dance that has continued for millions of years. The next moment it will be gone, utterly and completely gone, replaced by an expanding fireball of nuclear ash, a sphere of light and debris rushing outward at 10,000 kilometers per second, engulfing the red giant, vaporizing the accretion disk, and flooding the surrounding space with radiation intense enough to outshine the combined light of every other star in the galaxy. The transition from existence to annihilation will take less than 2 seconds. 2 seconds to unmake a star that took billions of years to form. 2 seconds to convert 1.4 solar masses of degenerate matter into an expanding cloud of iron, nickel, silicon, and pure energy. 2 seconds to produce a flash of light that will be visible across the observable universe for weeks. 2 seconds. That is the timescale of a Type Ia supernova. The build-up takes millions of years. The eruptions take days. The accretion takes decades. But the final act takes 2 seconds. And when it is done, The system that was RS Ophiuchi will cease to exist. The white dwarf will be gone. The accretion disk will be gone. The red giant companion will be stripped of its outer layers or kicked away entirely by the asymmetric blast. The constellation Ophiuchus will briefly host the brightest object in the galaxy, and then, over the following months, the light will fade, and all that will remain is a slowly expanding shell of debris, cooling and mixing with the interstellar medium, eventually becoming invisible, eventually becoming indistinguishable from the ordinary gas and dust of the galaxy. The atoms that were once a white dwarf will be scattered across light years of space, and in time, some of those atoms will be gathered by gravity into new cloud, new stars, new planets, and perhaps new life. That is the deeper truth. Not just death, but transformation. Not just ending, but recycling. The universe does not waste its material. It merely rearranges it through processes of staggering violence and exquisite patience into ever-new configurations. And RS Ophiuchi, whether it detonates tomorrow or in a billion years, will be part of that rearrangement. What does RS Ophiuchi mean for humanity? Not in practical terms. We are not in danger from this system. The probability that it will produce a Type E supernova within the next million years, let alone within a human lifetime, is small. The effects on Earth, even if it did, would be scientifically spectacular but physically harmless at a distance of 5,000 light-years. The question is not about physical danger. The question is about meaning. We live in a universe where dead stars can reignite, where a remnant the size of Earth, with the mass of the Sun, can steal fuel from a bloated companion and detonate repeatedly over thousands of centuries, where the debris from these detonations is spread across light-years, mingling with the gas and dust that will one day form new worlds. This is the universe we inhabit. It is violent and patient in equal measure. It builds slowly and destroys quickly. It creates complexity from simplicity and returns complexity to chaos. And it does all of this without purpose, without plan, without awareness. The realization that we live in such a universe is, for some, deeply unsettling. For others, it is profoundly liberating. There is no script. There is no cosmic narrative that guarantees a happy ending. There is only physics operating at every scale from the subatomic to the supergalactic, producing outcomes that are predictable in principle, but astonishing in their specifics. A white dwarf accreting hydrogen from a red giant is not a story. It is a process. But we turn processes into stories because that is what we do. We are the storytelling species. And the story of RS Ophiuchi, whether we frame it as a tale of destruction or of creation, of threat or of opportunity, of fear or of wonder, is ultimately a story about us, about what we notice, about what we choose to study, about what we consider important. Consider this. Of the approximately 400 billion stars in the Milky Way, only a handful of recurrent novae are known. Of those, RS Ophiuchi is among the best studied. The total number of human beings who have dedicated significant portions of their careers to studying this system is probably fewer than a few hundred. The total number who have made major contributions to our understanding of it could fit in a single conference room. These are the people who have tracked the eruptions, analyzed the spectra, run the simulations, published the papers, and debated the interpretations. They are the keepers of the knowledge, and through their work, they have connected one flickering point of light in a crowded star field to the deepest questions in science. This is one of the most remarkable aspects of the scientific enterprise. A small number of dedicated individuals, working with limited resources and imperfect instruments, can unravel the behavior of a system 5,000 light-years away and connect it to the fundamental structure of the cosmos. The leverage of understanding is extraordinary. A single well-placed observation, a single clever analysis, a single theoretical insight can shift our understanding of the entire universe. Newton saw an apple fall and derived the law of gravity. Chandrasekhar sat on a steamship and calculated the maximum mass of a white dwarf. Perlmutter, Schmidt, and Rias observed a few dozen distant supernovae and discovered that the universe is accelerating. Each of these moments was small in scale but enormous in consequence. The next such moment may come from RS Ophiuchi. The next eruption, expected sometime in the mid-2030s, will be observed by instruments that did not exist during the previous eruption. New telescopes, new detectors, new computational tools will extract information that was previously inaccessible, and the data from that eruption, combined with the data from the 7 previous eruptions, may finally resolve the questions that have driven research on this system for more than a century. Is the white dwarf gaining mass? How fast? Is the single degenerate channel a viable pathway to type supernovae? And what does this mean for the standard candle, the distance ladder, and the evidence for dark energy? The answers will not come from RS Ophiuchi alone. They will come from the combination of observations of all recurrent novae, all type Ia supernovae, all progenitor candidates, and all the theoretical and computational work that ties them together. But RS Ophiuchi will be at the centre. It has always been at the centre, ever since Williamina Fleming noticed its eruption on a glass photographic plate more than a century ago. There is a lesson in this, one that extends beyond astronomy. The lesson is that understanding accrues slowly, through the patient accumulation of observations and insights over long periods of time. No single eruption of RS Ophiuchi tells the whole story. No single observation resolves the debate. It takes many eruptions, many observers, many instruments, and many decades of work to build a picture that is complete enough to be useful. Science is not a series of lightning bolts of genius. It is a steady construction project, brick by brick, observation by observation, hypothesis by hypothesis, built by many hands over many generations, and the construction is not finished. We are still adding bricks. Each eruption is a new brick. Each observation is a new brick. Each simulation, each calculation, each paper published and debated and revised is a new brick. The structure is growing, and it is beginning to take a recognizable shape. But we cannot yet see the finished building. We do not know what it will look like when it is complete, and we may never see it completed because the questions raised by RS Ophiuchi connect to questions that may take centuries or millennia to fully resolve. This is humbling, but it is also beautiful. The fact that we can participate in a project of understanding that spans generations, that the observations we make today will inform the theories of tomorrow, that the questions we ask now will shape the research of the future, is a testament to the cumulative power of human curiosity. We are not solving the puzzle in one sitting. We are contributing to a mosaic that our descendants will continue to assemble, and they will have better tools than we do. They will have telescopes that can resolve individual stars in distant galaxies. They will have detectors that can capture single neutrinos from nova eruptions. They will have computers that can simulate the entire life cycle of a binary star system from birth to death. They will have datasets spanning centuries of observations, compiled and curated by generations of astronomers. And they will look back at our work, at the observations we made of the 2021 eruption, at the models we built, at the papers we wrote, and they will see our contributions as early and imperfect steps in a much longer journey. That is not a diminishment. That is the nature of science. Every generation stands on the shoulders of the last. Every observation, however imperfect, adds to the total, and the total, accumulated over time, becomes something greater than any individual contribution. The understanding of RS Ophiuchi that exists today is the product of hundreds of researchers working across more than a century. The understanding that will exist a century from now will be the product of thousands more, and somewhere in that future understanding, the answers we seek may finally emerge. What will those answers mean for our place in the cosmos? Perhaps nothing, in a practical sense. The universe will continue to expand, whether or not we understand the standard candle. Dark energy will continue to dominate the energy budget, whether or not we can measure it precisely. RS Ophiuchi will continue to erupt, whether or not anyone watches. The physics does not depend on our comprehension, but comprehension matters to us. It is, in a sense, all that matters to us, because it is the only thing that distinguishes us from the unconscious matter that surrounds us. A rock does not wonder about its origins. A gas cloud does not calculate its own density. A white dwarf does not contemplate the Chandrasekhar limit. Only we do these things, and in doing them, we transform the universe from a meaningless collection of particles and forces into something that can be known, described, and wondered at. RS Ophiuchi does not need us, but we need RS Ophiuchi. We need it as a laboratory, as a test case, as a calibrator, and as a reminder that the universe is active, not static, that the processes shaping the cosmos are ongoing, not complete, that the same nuclear physics that forged the elements in our bodies is still at work, 5,000 light-years away, building toward an explosion that will scatter new elements across new reaches of space, and that we, for this brief moment in cosmic time, have the privilege of watching. Pause for a moment and consider the sheer improbability of this situation. A planet forms in the habitable zone of a stable star. On that planet, over billions of years, chemistry becomes biology, biology becomes complexity, and complexity becomes awareness. That awareness develops language, then mathematics, then instruments capable of detecting photons from thermonuclear explosions 5,000 light-years away. The beings who build those instruments use the photons to reconstruct the physics of a system they have never visited and will never visit. And from that reconstruction, they derive insights about the structure of the entire observable universe. The chain from hydrogen atom to human astronomer is unbroken, and every link in that chain is governed by the same laws of physics that govern the white dwarf in RS Ophiuchi. We are not separate from the cosmos. We are the cosmos, organized into a form that can reflect on itself. And when we study RS Ophiuchi, we are not studying something alien. We are studying the same physics that made us possible, the same nuclear reactions, the same gravitational forces, the same quantum mechanical principles. The white dwarf in RS Ophiuchi is our distant cousin, made of the same quarks and electrons, governed by the same equations, bound by the same limits. The difference is not in the physics. The difference is in the arrangement. And the arrangement, in our case, happens to permit curiosity. That curiosity has led us here, to this moment, to this understanding. It has shown us a dead star that erupts like clockwork, a system that may be building toward the most powerful class of stellar explosion known, a connection between one binary star and the measurement of the entire cosmos, and a reminder, always a reminder, that the universe is not finished. It is still in the process of becoming, and so are we. There is comfort in that. Not the comfort of safety, not the comfort of permanence, but the comfort of participation. We are participants in a process that began 13.8 billion years ago and will continue for trillions of years into the future. Our participation is brief, a few centuries of modern astronomy, a few millennia of recorded stargazing, a few million years of existence as a species, but it is real, and in that brief participation, we have come to understand things that the universe itself, in its unconscious operation, will never know. We know what a white dwarf is. We know what the Chandrasekhar limit means. We know how novae work, and why they recur, and what they might become. The universe does not know these things. Only we do. And that knowledge, fragile and imperfect as it is the most extraordinary product of the cosmos. More extraordinary than any star, any galaxy, any supernova. It is the universe, looking at itself and understanding what it sees. And perhaps that is the most important implication of all. Not what RS Ophiuchi means for cosmology, or for element synthesis, or for the standard candle, but what it means for us. It means that we are part of a universe that can be known, a universe that yields to inquiry, that reveals its secrets to those patient enough to look, and that rewards curiosity with understanding. RS Ophiuchi will do what physics demands. It will accrete, erupt, and perhaps one day detonate. Our role is simply to watch, to measure, to think, and to wonder, and that, for beings as temporary as we are, is more than enough. In the constellation Ophiuchus, the serpent bearer, there is a point of light so faint that you cannot see it without a telescope. It does not draw attention. It does not announce itself. It sits among millions of other faint points in a crowded region of the Milky Way, unremarkable to anyone who does not know where to look or what to look for. It has no name that most people would recognize. It appears in no popular sky guide, on no planetarium ceiling, in no constellation myth familiar to school children. It is by all outward appearances nothing, but it is not nothing. It is RS Ophiuchi, and it is one of the most extraordinary objects in the galaxy. It is a dead star feeding on a dying star, a white dwarf stealing fuel from a red giant, a system caught in a cycle of theft and explosion that has repeated at least 7 times in recorded human history, and will repeat again. Each eruption is a thermonuclear detonation on the surface of a stellar corpse. Each eruption ejects material at thousands of kilometers per second. Each eruption for a few days makes the system visible to the naked eye, a ghost appearing in the sky before fading back to invisibility. And each eruption leaves the white dwarf a little heavier, a little closer to a limit, a little nearer to a detonation that would be not a surface flash but a total annihilation. The Chandrasekhar limit, 1.44 solar masses, a number calculated by a young man on a boat nearly a century ago. A number that determines the boundary between a quiet death and a violent one. A number that connects the quantum mechanics of electrons to the brightest explosions in the universe. And RS Ophiuchi is approaching it. Slowly, patiently, eruption by eruption, grain of hydrogen by grain of hydrogen. We do not know when it will arrive. We may never know, because the timescale may exceed the lifespan of our species. But the process is underway. The evidence is strong. The trajectory is clear, and the implications, should the white dwarf cross that line, extend from the local interstellar medium to the farthest reaches of the observable cosmos. Type Ia supernovae are the standard candles by which we measure the universe. They are the yardsticks against which we gauge the distances to galaxies billions of light years away. They are the tools that revealed the accelerating expansion of the universe and the existence of dark energy. And RS Ophiuchi may be one of the systems from which those candles are made. Understanding it is not optional, it is essential. Because if we misunderstand the candle, we misunderstand the distance. And if we misunderstand the distance, we misunderstand the cosmos. This is the weight of a small flickering star. It carries in its repeated eruptions information about the nuclear physics of degenerate matter, the dynamics of mass transfer in binary systems, the mechanisms of particle acceleration, the synthesis of heavy elements, and the reliability of the cosmic distance ladder. One system, one binary star, one dead, feeding, erupting, resilient, dangerous white dwarf, and from it, a thread that connects to everything. We began this journey with a question. What is RS Ophiuchi? The answer, as we have seen, is not simple. It is a recurrent nova, one of fewer than 10 known in the Milky Way. It is a binary star system, consisting of a massive white dwarf and a red giant companion. It is a laboratory for studying thermonuclear explosions on degenerate surfaces. It is a potential Type Ia supernova progenitor. It is a cosmic ray accelerator. It is a test case for the standard candle hypothesis. And it is a reminder that the universe is active, ongoing, and far from equilibrium. But perhaps the most honest answer is the simplest one. RS Ophiuchi is a star that will not stay dead. It was born, it lived, it exhausted its fuel, and it died. It became a white dwarf, a dense ember cooling in the dark. And then, through the accident of having a close companion, it found a new source of fuel. It began to feed. It began to erupt. It began a second life, a violent and temporary renaissance powered by stolen hydrogen. And now, with each eruption, it drifts closer to the threshold, beyond which the renaissance ends and the final destruction begins. It is a story of death, resurrection, and ultimate obliteration. A story told not in words but in photons, in X-rays, in gamma rays, in the spectra of expanding gas and the light curves of thermonuclear explosions. A story that has been unfolding for longer than human civilization has existed and will continue long after the last human has gone. The universe tells stories like this all the time. In every galaxy, in every star cluster, in every binary system, where a white dwarf orbits close enough to a companion to steal its substance. These stories are silent. They have no narrators. They have no audiences, except when a civilization arises that is curious enough to build telescopes and patient enough to watch. We are that civilization, and RS Ophiuchi is one of the stories we have chosen to follow. The next chapter will be written by the white dwarf itself, in the language of nuclear fire, sometime in the next decade or two. We will be ready. Our telescopes will be pointed. Our detectors will be primed. Our models will be waiting. And when the eruption comes, we will capture every photon, every spectrum, every data point, and we will add it to the century of observations that came before. And then we will wait again for the next eruption, and the next, and the next. Each one a step in a journey whose destination we can calculate but cannot see. Each one a heartbeat of a star that refuses to go quietly. In the constellation of the Serpent Bearer, hidden among the millions of stars that line the plane of the Milky Way, A dead star is feeding. It erupts and recovers, erupts and recovers, erupts and recovers. Each cycle is a small violence. Each cycle is a small accumulation. And each cycle brings the system one increment closer to a violence that is not small at all. The white dwarf does not know this. The red giant does not know this. Only we know. Only we can calculate the limit, measure the approach, and comprehend the consequence. And so we watch, we measure, we wonder. We are the universe's consciousness, briefly flickering, briefly aware, trying to understand what it means for a dead star to keep burning. One day, the burning will end. Either the fuel will run out, and the white dwarf will cool for eternity, or the limit will be crossed, and 2 seconds of thermonuclear fury will unmake a star. Either way, the story will continue. New atoms will join the interstellar medium, new clouds will form, new stars will ignite, new planets will coalesce. And perhaps, on one of those planets, new eyes will look up at a sky that no longer contains RS Ophiuchi and will wonder, as we do, what was there before. For now, it is there, quiet between eruptions, patient, accreting, building, a small point of light in a vast and indifferent cosmos, a dead star with a pulse, a heartbeat measured not in seconds but in decades, a rhythm that has continued for millennia and will continue for eons. And all we can do is listen. Listen to the photons that arrive after 5,000 years of travel. Listen to the X-rays that tell us the surface is burning. Listen to the gamma rays that tell us particles are being accelerated to nearly the speed of light. Listen to the radio waves that trace the shape of the expanding shock. Listen to the infrared glow of dust formed in the cooling debris. Every wavelength is a voice. Every observation is a word. And the sentence they spell out, when we piece them all together, is both simple and profound. A star is dying. Again and again and again. And each time, it comes back a little heavier, a little closer to the edge, a little more dangerous. The pattern is clear, the trajectory is set, the physics is inexorable, and the only question left, the question that will outlast every one of us, is when the pattern breaks, when the recycling stops, when the eruption becomes not a nova, but a supernova, when the pulse becomes a final beat. We will not be there to see it. In all likelihood, no human being alive today will witness the crossing of the Chandrasekhar limit by the white dwarf in RS Ophiuchi. The timescale is measured in millions of years, and we are creatures of decades. But the process does not need us. It does not require our attention. It will proceed whether we watch or not, whether we understand or not, whether we exist or not. And that, perhaps, is the most fitting end to this story. Not an answer, but a continuation. Not a resolution, but an ongoing process. Not an ending, but a pause between eruptions. Somewhere in the constellation Ophiuchus, right now, hydrogen is falling onto the surface of a white dwarf. The temperature is rising, the pressure is building, the fuel is accumulating, and when it reaches the critical point, the surface will ignite again, and a familiar star will blaze back to visibility, and the astronomers will look up and the cycle will continue. The universe has no endings, only transformations. And RS Ophiuchi, for all its violence and all its danger and all its cosmic significance, is simply one transformation among trillions, one cycle among countless cycles, one heartbeat in a universe that has been beating since the beginning of time and will continue beating long after the last star has gone cold. We are fortunate to hear it, we are fortunate to understand it, and we are fortunate, most of all, to be alive in a moment when the heartbeat can be measured, the cycle can be tracked, and the meaning, such as it is, can be contemplated by minds that emerged from the very same processes they seek to comprehend. A dead star with a pulse, a universe with a rhythm, and a species, brief and brilliant, listening in the dark.